Good morning to all remote centers and the participants available at ETV studio. Today is the fourth day of the ICT 21 program on optical fiber communication. Today we have invited our most learned expert, Dr. B.C. Chaudhary. Dr. B.C. Chaudhary is the professor and head of the applied sciences. In general, in electronics, it has been found if the person is very good in teaching, he is very poor in practical. If he is very good in practical, he is very poor in teaching. But B.C. Chaudhary is one of them. He is both theoretical and experimental and has set up very good optical fiber lab. And sometime, if you get chance, the students of NITTTRCHD as well as the remote centers, please visit the Applied Sciences Laboratory of Optical Fiber. It's one of the very good laboratories. So I request Dr. B.C. Chaudhary to take the session, and during the session, if somebody asks the practical question, I request you to please reply them because you are the very good practical hand person. So participants at the studio as well as the remote centers may ask the relevant questions related to the field. Thank you.
Thank you, Chan sir. And good morning to all the participants at studio as well as different remote centers. Myself, B.C. Chaudhary, I'm professor in applied physics and I'm working in the area of fiber optics, optical fiber communication, and also teaching this subject at different stages. So I hope in the previous sessions, most part of the related to optical fiber technology has been covered. So I will, this session is on optical fiber systems, design and analysis. So I will consider only the design aspects and different analysis part. Mostly I will try to touch the practical aspects. So I hope you all know that in any optical communication system, there are basic three components. One is the optical transmitter, optical receiver, and then optical fiber. So even in optical transmitter, if you analyze it, all the part is electrical. It is same as per your, except at the end you have a optical source. So optical source, it will convert electrical signal to optical signal. Now this optical signal, it will travel over the optical fiber, and again at the receiver end, the optical signal is converted to electrical signal by optical detector. Now depending upon the conditions of the signal may be amplified, it may be reshaped, or whatever is the requirement, because user need the right kind of signal.
Hello.
So when we are looking for the link, we consider only point-to-point link, where we have a blunt transmitter, fiber, and depending on requirement, if it is a long distance requirement, the system may repeat. You all know in an electronic communication system, if there are power losses, we go for amplifiers. If there is broadening of the pulse, or what you call in optical fiber, we call it the dispersion. So it means pulse is broadened. So it will affect your data rate. So we have to correct for that. We may go for the retiming of the signal, reshaping of the signal, because in digital you need a rectangular pulse. So all these processes have to be considered. So OFC system, it is in this part you have a transmitter and you have a receiver. And I mentioned I will discuss only point-to-point link. OFC is mostly used as a point-to-point link from user to the destination. So I already discussed, you have electrical to optical conversion by optical source, and then optical to electrical conversion by optical detector. I hope somebody must have covered all these two parts. Then we have the optical fiber, and in between there may be different components. It may be connector, it may be supplies to make a permanent joint to optical fiber. There may be a coupler to couple fiber to the optical source or fiber to the detector or the distribution of the signal. So number of optical components may be there. And we know whenever there is any component, there is always some loss. So some difference loss or different parameters are always there. So when we have to design a link, we are concerned with the two parameters. I hope you know. One is the attenuation. You are designing a link, it may be a short haul link when we discuss about maybe a few kilometer or few meter. Then it can be a mid haul link. You may go up to maybe 10 kilometer or 15 or 20 kilometer, or it may be a long haul link. So when we talk about the telecommunication, it is a long haul link. Long distances are there. And I hope you know in optical fiber, the attenuation, the signal can travel up to how many kilometer? Approximately. It can travel around 100 kilometer without any repeater. Repeater is basically your amplifier, or it is a complete circuit. So in a repeater, you have a detector, then the signal is extracted, it is amplified, put over the optical transmitter. So it is a full system, but in the reverse order. So repeater costs a lot. If you have a copper cable or coaxial cable, the repeater spacing is maybe around 3 kilometer. Whereas in optical fiber, in present day optical fibers, the signal can travel up to 100 or 150 kilometer without any repeater. Even the first OFC link, which was started in 1977, the repeater spacing was 9 kilometer. So nowadays you can say how many the cost saving is a lot. Similarly, another part is the broadening of the pulse, or in light we call it as the dispersion. So data rate depend upon the size of the pulse. Narrow is the pulse, more is the data rate. You may call about the kbps, mbps, gbps, or now the terabits per second. This is the requirement today. In OFC we talk about the terabits per second. So all these, in order to fulfill these requirements, what is required? We have to measure. You need the measurements. So design and installation, it needs the measurements. So you should have certain data. When you are planning for link, you have certain goals and you need lot of calculations. They are only possible if you have data. So we need measurements, or what you call it the operational characteristics of constituent components. And of particular importance is the optical fiber, because your transmitter and your receiver, they are lying in very, very comfortable environment, air conditioned room, and it is at one place only. Optical fiber is in the field. It will face all sort of external turbulences. Whatever is the problem is only with the optical fiber. There may be vehicle passing over the optical fiber. It may be in some hazard environment, lot of high tensions are all there, EMI is there. So it faces even lot of construction work is there. Every day you read in the newspaper, during digging the fiber is damaged. So all these phases are faced by optical fiber. So optical fiber is the most important component of this link, and its accurate and precise measurements are very, very important. And mostly who are interested in these measurements, either manufacturer or system engineer, because manufacturer has to provide a optical fiber with certain parameters. There are certain specifications. If you are mentioning about numerical aperture, say 0.2, it has to be 0.2. Refractive index of the core, relative refractive index, all these parameter, or attenuation, how much is the attenuation? So he should have the values with him. So he will be interested in measurements. Similarly, system engineer, he have to design. If he have to design a link of say 100 kilometer, he know optical fiber, the losses, and if he is working at 1550 nanometer window, the losses will be around 0.2 dB per kilometer. So he can calculate how much distance the optical fiber, the signal can travel. So all these calculations, they are very, very important for system manufacturer as well as system engineers. So you know, I hope you know optical windows. Optical fiber optic is working mostly three windows. One is the 850 window, other is the 1310 window, then we have the 1550 nanometer window. It started with the 850. It is not only that light is available in this region, you know the electromagnetic spectrum, but you need the optical sources, you need the optical detectors. Problem with detectors is not a sphere because detectors are broadband detectors. They can detect the signal from 800 to 1500 by single detector. But source is very, very specific. Earlier you have the LEDs or you have the lasers, what you call as the laser diodes. So they were not available in this region. So someone have to do research and to develop these optical sources. So they were developed in this manner. So now we have standard 850 window is not very, very, you can say, attractive now, because here losses are very, very high, around 5 dB per kilometer. At 1310 nanometer, around 5.5 dB per kilometer, and 1550 is the window with least loss. So 0.2 dB per kilometer. So mostly 1310 and 1550 windows are very, very attractive. So these are the all system requirements I mentioned. Link length. How much is the link length? What is the repeater less distance? Lesser the number of repeater, lower will be the cost. Specifically nowadays, communication is a very, very challenging job. It is not only the quality, you need very, very high quality. You need very, very high capacity, but you are not ready to pay more. Economy is there, lot of competition is there in the market. Last week, this Jio, they started a scheme with very, very low cost. BSN has to come out with same. Otherwise, you cannot survive in the market. So, cost is a very, very rigid constraint in this area. So, link length and then maximum transmission rate, whether it is Mbps, Gbps or terabits per second. So, these are the two goals a designer has to achieve, and all the system requirements, they depend upon these two goals. So depending upon these, he have to choose type of input, type of data, and you know it can be analog, it can be digital. Mostly nowadays we talk about the digital signals. Type of data are there. You can have RZ, you can have NRZ, you can have Manchester coder. So many type of digital data are there. So one have to choose that. Then transmitter. But type of detector, it can be LED or it can be ILD. How much is the launch power? That will also depend upon the distance. It is not that if you have to cover 10 kilometers, you choose a laser of very, very high power, because that will cost. So you have to optimize all these components, launch power and type of modulation. Mostly we go for the intensity modulation in here, but different type of modulations are also there. Accordingly, that will also come into consideration. Then optical fiber cable and the receiver. Mostly parameter in the receiver is the sensitivity. So you can have either pin detector or it may be a APD. So sensitivity is the minimum power required for the detector to operate. If power received at a detector is less than the minimum power required, it will not operate. So one have to decide all these components. So optical transmitter, I already discussed. The role is to convert optical signal to electrical signal. It has the optical source. So even in the optical source, one has to decide either LED, laser or LED. If it is a laser, it will give you very, very high quality data, but cost is also more. Maintenance is also more. They are very, very sensitive to external environment. LEDs, of course, they are low cost. They have high reliability, but they cannot handle high data rate. They will give you more broadening or more dispersion. So one have to decide. Similarly, cable. You should know how much light can be coupled into optical fiber, numerical aperture. Then how much attenuation is there, how much dispersion is there. All these parameters are required, because you started with some definite signal. Let it be a peak, say 5 volt 50 picosecond pulse. At the receiver you should also get similar type of pulse, around 5 volt and around 50 picosecond, because system is optimized for standard data. So one have to see now optical fiber whether multimode or single mode. In single mode there is least dispersion, whereas in multimode there is more dispersion. Multimode can carry more power, single mode cannot carry more power. Most of non-linear effects may be there in the single mode. So again, depending upon the requirement, so multimode or single. Then glass or plastic. So fibers, you have different type of fiber made from glass. You can have silica cleared silica, you can have plastic cleared silica, you can have total plastic fiber. So again, performance differ. Glass is the best quality. So one have to decide about the cable. Then receiver. The role of receiver is to convert optical signal to electrical signal, and it houses the photodetector major component. The optical component is photodetector. So again, in that category, I hope you know there are two type of detector which are in use. One is the pin. It is similar to your PN diode, but it has large intrinsic region. So PIN. Another is the avalanche photodiode, APDs. The difference is in pin there is no internal amplification, whereas in APD there is internal amplification or multiplication of the signal. So they have very good sensitivity. They can work at very low power. So if you are working with a pin, you may power of the order of microwatt, whereas for APDs even nanowatt of power is sufficient. But there are again limitations. Pin they require they are low cost and they work with normal typical power supplies 5 or 15 volt, whereas APDs, this is a device with much better sensitivity, even more than 5 to 10 dB sensitivity. They have twice double the bandwidth. However, they cannot be used with the normal power supplies. You need the high power supply. Maybe initially it was maybe around 200 volt or 150 volt, but now they have come even up to 40 volt or 50 volt. So when you need more high power, you have to design a circuit. And APDs are usually found in the long haul link, because in the long haul link power will fall. So again the choice pin and APD. APDs are best sensitivity wise, but they have more problems also. When there is a multiplication, they add noise also. We call it the excess noise. So again, choice of combination LED or pin. It is a very economical system. You can have LED or APDs. You can have laser and pin, or laser and APDs. High performance system, but high cost also. So one have to decide all these parts. Then connectors. Number of connectors are required in between. So we have to look for the connector. Different type of connectors are there in fiber optics. They differ in performance. They differ in quality. They differ in reproducibility. So all one have to decide about the connector, because at each connector some loss is there. It may be very small, but always some loss is there. Then when we design a link, we have to look for different parameters. So all these components, you should have data available with them. Then one have to look for all the components. You know, when you are designing a link, one have to look for different factors, all of which contribute to final goal of ensuring the desired signal at the receiver. But out of all these components, the most important component is the receiver, or deciding component is the receiver. Because whatever is your LED optical source, high quality, you have high quality fiber. If the right amount of power will not reach at the receiver, it will not work. So without right amount of light, the entire system will not operate properly. So receiver sensitivity is very, very important. So one have to look for this part, and if you know, in this part you have an optical transmitter, you have an optical receiver, and in between optical fiber, connector, and all whatever you call, whatever is required in between. So you know, optical transmitter, it has certain power. You call it as the launch power. How much power is delivered from the optical transmitter? Now this power will be coupled to optical fiber. And you know, optical fiber, what is the size of single mode optical fiber? Diameter. So around 8 to 10 micron. Whereas your optical device, laser, it will be of higher, bigger size. So when you couple the two, there is a lot of loss. Same is the condition with the detector and optical fiber. So fiber to fiber joint is not a problem. Both are of same size, but here size are different. So as a result, there is a lot of loss. If you connect a bigger water pipe to smaller water pipe, lot of loss will be there. But on the other hand, if you are connecting smaller pipe to bigger pipe, all the water can be transported to bigger pipe. So detectors are larger in size. Losses at fiber to detector coupling are less, whereas source to fiber coupling, higher losses are. So one have to look for all those aspects. So you have some power. Then on the other hand, you need some minimum power. So two parameters are defined. So the rest in the difference of two, that can be consumed. So we call it budget. It is a power budget. All we salaried class, we have a budget. I have this much salary, I need this much amount to pay the EMI, to pay the tuition fees of my son or all other parts, and rest of जो हमारे पास बच जाता है, that we can decide कि इसको कैसे खर्चना है. Same is the part here. So you have some power from the transmitter, you need some minimum power, and rest of the power can be consumed in between the link. So this is what are our budget. So all these parameters are required. We have to look for all these step by step, and we have to calculate what is the total optical loss in the system by adding cable loss. Now there will be loss in the cable, there will be supplies loss, there is connected loss. So all these loss, they have to be added, and this loss should not be more than the difference of power between transmitter and receiver. That is, you start with say 40 dBm of power, you need 10 dBm of power at the receiver. So 30 dBm power can be consumed by these components. So we design it like this. So these parameters should be available with the manufacturer. If you don't know what is the loss, fiber loss, or what is the supplies loss, what is the connected loss, you cannot calculate this. So all these measurements are required. So you compare the loss figure with the allowed optical loss. How much loss is allowed? So we calculate the loss of all the component, then compare with the allowed loss. So if it is more, we have to go for redesigning of the system, or we have to change the components. On the other hand, if it is within the allowable loss, your system is acceptable, your design is okay. So first we go for the power budget. सबसे पहले आपकी रिसीवर पे पावर पहुंचनी चाहिए. Next is your quality of data. So then if you have a sufficient or allowable link power at the receiver, then we check for the fiber bandwidth or data rate, whether it is adequate or not. You are working at certain say 10 Mbps, it should be there. For 10 Mbps, you can calculate what should be the width of the pulse. So accordingly, one have to go for the second check. So first check is the power, second check is, we call it as the time budget, timings. So time of the width of the pulse or timing of the pulse. So power budget and time analysis. Both are the design calculations. So after performing above calculations, if it is discovered that the fiber bandwidth is inadequate, we have to change the company. Either you change the fiber, you change the transmitter, you change the data type, something has to be changed. So you cannot bypass these calculations. Okay. So these are all data sheets. They have to be, should be available with the designer. Before you design the system, you all go for the what are the specifications for diode, for transistor, for IC. All parameters are there. So I should have all the parameters. Then only I can perform the calculation. So first I mentioned we go for the link power budget because power should reach there. Then rise time budget. So time will rise. You know, in a pulse you have a rise time, you have a fall time. So if the pulse is broadening, so rise time will increase. So first, you see, if it is a rectangular pulse, rise time is very a single line. But if it is a broadened, so it will take some shape. It will take some Gaussian type of shape. So rise time will increase, and we always measure how much rise time? 80%. What is the 80% rise time of the pulse? Because 100% is not possible. Lot of noise will be there. Noise at the top, noise at the bottom. If you have a binary signal 0 and 1, what is 0 means? What is the voltage of 0 signal? 0 signal means in terms of voltage. So it may be from minus 1 to 1, and signal 1 it may be 3.5 to 5.5. So you call it the high signal and low signal, and at the top and bottom there will be always a noise. So we always look for the 80% rise time. So link power budget, I mentioned, it determines the power margin between the transmitter and minimum receiver sensitivity, and it is always defined at certain parameter, quality of the data. The quality of data is decided by either in analog form we call it signal to noise ratio, or we call the quality factor, or we call the BER, bit error rate. In digital system we deal with the bits, bit error rate. How many bits are erroneous? If you are talking about say 10 to the power 9 bits you are sending, how many bits are false? Instead of 0 it is 1, because if the signal amplitude rise, if the signal amplitude of 0 signal say from 1.5 it goes to 3.5, it will be counted as 1 signal. Similarly, if 1 signal come below 3.5, it will be counted as 0 signal. So there is an error in the signal. Error may be in 1 or maybe in 0. This is error. So error over total bits, bit error rate. Maybe -9, -12, -20, -4, -5, whatever it is always in this form. So 10 to the power -9 BER means 1 error in 10 to the power 9 bits. If you are sending 10 to the power 9 bit, 1 bit can be in error. So these type of qualities are required. So we calculate all these margins in the power budget, and then if there is a problem we look for all these parts. So again coming to original figure, so you have a transmitter, you have a receiver, you have say let there be some minimum power say PS, so minimum power required is PR. So in between number of components are there. You are connecting fiber to the source, some loss will be there, let's say it is defined as LC loss. Similarly connector to fiber to detector loss, LC, because these are the two losses at only 2 points, they are not link dependent, whereas in between your attenuation it is link dependent, dB per kilometer. Connectors, they are link dependent. Supplies, joint, it is also link dependent. It depends how much length of fiber is available. Attenuation you are talking about 100 kilometer, but if you go in the market you will not find fiber cable more than either 4 kilometer or 5 kilometer, mostly 2 kilometer, because it is a cable, it is not 10 micron or 125 micron. Now a cable with lot of strength, it will go to field. There is a difference in optical fiber and optical fiber cable. Number of protective layers are there over the optical fiber. So as a result, so it means after every 4 kilometers you have to make a joint. So it is link dependent. So all these parts are link dependent. I can calculate this loss. What is the available power? So PS minus PR. And in this case, you have two connectors which are fixed, and the rest is the length dependent loss. You can add source, supplies, and total loss as a length dependent. So you can calculate how much is the length dependent loss, how much is the fixed loss. Then of course we always go for system margin. System margin is because your parameters, they may not be perfect. All the parameter specification which you will get, how they are measured? They are measured in a laboratory where all the conditions are perfect. But ultimately these components, they will go to the field. So we always go for the margin. And these margins are generally 6 dB for LED and 8 dB for laser. ILD, injection laser diode. Because there are more fluctuations in laser and more power also. So this margin we have to keep. So all this has to be added. So you have a loss, LC loss, you have a fiber dependent loss, you have a system margin. All they have to be added, and this loss should not be more than PT. All these calculations have to be performed. So once you get the power budget, you get the loss, that all the system loss is within the limit, then we go for the right time budget. So first requirement is the power budget. We go for the right time budget. So once the link power has been established, the designer can perform the right time analysis. So now you have a certain standard data, digital data, it will go to the transmitter. So there will be modulation. Some right time will be there. Then it will go to the, maybe on the fiber. You know, in the fiber there is a different type of dispersions. Intermodal dispersion, intramodal dispersion, material dispersion, waveguide dispersion, different type of dispersions are there. They will broaden the signal. So as a result, now after fiber, it will go to different components. It may also affect the signal. It will go to the receiver. There is a demodulation or amplification. It will again affect the signal. So ultimately, whatever data you get, your pulse may be broadened. You started with 50 picoseconds pulse, at the end it may be 70 picoseconds. It is not desired form. So data rate means in 1 second how many bits can be accommodated. When you are talking about gigabits, it means you have to accommodate 10 to the power 9 bits in 1 second. If you are talking about kbps, 10 to the power 3 bits in 1 second. So bits of the pulse is very, very important for data rate. So we calculate all these parts. So it is always, it is given by root mean square. All the variations, they are added in root mean square. It is not that one is positive, other is negative, you add it is 0. It is not like that. We have to square these and we go for the RMS. Just like you are traveling on the road. Whether you go on the left side or you go on the right side, you will fall. It is not that going left and right and it will not happen. So pulse, it has to be a optimized, standard optimized pulse. It should remain 50 picosecond. If it is less than picosecond, your system will not behave properly. If it is more than 50 picosecond, again it will not behave properly. So standardized, this is what we call as the optimization. Standardization or optimization. So all these parts I mentioned, they are transmitter rise time, it will go to the transmitter, group velocity dispersion, GVD, model dispersion, if it is a multimode transmission, then rise time in the fiber, receiver rise time. All these are the major parts. There may be other parameters, but they are all basic component in any of the system. And we always measure, generally the rise time should not be more than 70%. We measure, you know the term, what is the duty cycle? For any digital signal, duty cycle is 50%, 50-50. And if your signal is distorted, the maybe the on time or off time, it will increase. So it will rise. So this rise should not be more than 70% if you are working with NRZ data. It should not be more than 35% if you are working with the RZ data. So we measure the duty cycle. So in any case, duty cycle should not be more than 80%. So that is the maximum limit. If it go beyond 80%, your digital data will not be a discrete data. There will be no difference in 0 and 1. It will be counted as either 1 or either 0. So right time budget we have to go. Just giving you the example, so you can have a link of 5 kilometer, data rate 50 Mbps at BER of 10 to power minus 9. For system, BER is defined. It is the user to decide the quality of data. I may be very happy with very poor quality of data. You may not be happy with that quality of data. So one have to define, I want this type of data. I want 2 Mbps at my telephone. I want 1 Gbps. That has to define, and at that there is a defined VER. Transmitter is LED 850 nanometer, 3 dBm is the power, and coupling loss is 5 dB. So when you couple fiber, generally your optical source is coupled to a fiber pigtail. Small length of fiber, it is coupled with the optical source. Because if you do that job in the field, you may damage the source, which is expensive one. So a manufacturer, he always provide what they call as electro-optic component. It has signal, it has a source, then small length of fiber over it. So now your job is connect fiber to fiber. So that's why some loss is there. Then multimode fiber of these dimension, transmitter to fiber, fiber to receiver, coupling loss is 1 dB. Then fiber optic cable has 1 supplies. Your supplies may be a fusion supplies, it may be a mechanical supplies. Then receiver pin sensitivity is minus 40 dBm. So it can accept power up to minus 40 dBm at 50 Mbps at this data rate. If data rate is in Gbps, you need more power. So power is also decided on the data rate. So we have to perform these calculations. Power budget. So you can have this type of budget table. So transmitter power 3 dBm, source to source coupling loss minus 5 dB. When you talk loss, it is minus, gain plus. Transmitter fiber optic cable 1 dB loss. It is mentioned given there 1 dB loss. Transmitter to fiber, fiber to detector 1 dB loss. So we have to consider. Then supplies loss. If supplies loss is given, then you can use it. Otherwise, it is generally taken as 0.25 dB for mechanical supplies, or it is in this range only. So 0.2, 0.3, 0.1, in this range it will be there. Fiber attenuation. Now wavelength is given. What is the loss in optical fiber? 850 nanometer, 4 dB per kilometer. Standard. So 5 kilometer link, so minus 20 dB. Then fiber to receiver coupling connector loss minus 1 dB. You add all these powers, so you will get minus 24.25 dBm. It means the difference PT, you have minus 24.25 dBm of power available. Now this power can be consumed. Now what is minimum power required as a detector? Minus 40 dBm. Which is more? Minus 25 or minus 40? So minus 25 is more power. So it means now you find the difference. So you have around 15.75 dB surplus power. So you are getting more power at the receiver. So you can consume this power maybe in further link, but remember you need safety margin also. So you are using the LED. So around generally given is 6 dB, but generally 10 dB power is taken as a standard margin in both the cases. So if you analyze this link, so you have a loss margin of 15, so margin is there. There is a margin of 15.75 dBm of power. So your system will operate very easily. So one can analyze it. You see here this much is the power available. So this is a good margin. So it depends. You can utilize this power. You can add 1 kilometer more. Even after 10 dB, 5 dBm power is available. So fiber loss is 4 dBm, 4 dB per kilometer. So your link can be up to 6 kilometers. So this one have to decide, this calculation one have to perform. So all this, because margin is required, because no matter how careful the power budget is, there is always some variations. So this power budget calculation is very, very important. Time is another parameter. So link analysis. So when you have a link, now you calculate the power budget, you have designed the system. System is put into operation. Now you have to monitor the system. It is not that once it is designed and forget. It is not like politics. Election में एक बार आए और 5 साल भूल गए. So one have to monitor it regularly. You are giving the services to the users. So now you see, in this example, it is a multi-link, but you see, when you have a source, there are variation in the source. Power output, optical spectrum, peak wavelength, pulse shape, extinction, so many parameters are there, which are associated with the source. They may vary. There should be some check. Similarly, connector or splice loss, it also varies with the passage of time. Multiplexers, generally for practical part, we use the number of signals and they are multiplexed. There may be variation in multiplexer. Then optical fiber, number of parameters, attenuation, dispersion, fault, so many things are there. Similarly, if the power is not sufficient at the receiver, we go for the amplification. We use the amplifiers. So when you use the amplifier, certain parameters are associated with the amplifier. I should know what is the gain, what is the noise, what is the operational status. Similarly, you reach at the demultiplexer. At the destination, you have to demultiplex the signal. You have to give the signal to individual users. Again, there are parameters associated with the demultiplexer. And during demultiplexation, you find some loss will be there. There will be loss. There will be what is the band pass. You may use the filters. Then even at the receiver, number of parameters are there. You have to check I diagram. You have to check what is the BER rate, what is the jitter. They are all associated with the noise, pulse rise time. So duty cycle. We have to measure what is the rise time of the pulse. All these parameters have to be measured if you have to monitor the system. Not only the power. Your component should be operational. These are the operational parameters. So, okay. So, in case you have any doubt, any query up to this part, you are most welcome. Otherwise, I will go for the testing part now. Any doubt?
Yes.
बताइए.
The single mode or multi-mode fiber difference. Not just according to the size and all, just according to the how much waves travel in single mode and how many waves travel in multi-mode fiber. So if can we say that the single mode fiber gives one-to-one communication, point-to-point communication?
They both are point-to-point communication. Both are point-to-point communication. But in a, you know, in a you must have gone through this light propagation in optical fiber, electromagnetic mode theory, number of geometric of the rays.
So can you give the example of single mode fiber where we use it application wise?
Mostly in telecommunication we use the single mode fiber.
Sir, but we say in single mode that only one wave can travel and only one-to-one communication is there at one time.
No, one-to-one communication is in both the cases. But in single mode, only one mode will travel. In multi-mode, number of mode will travel. For example, you are now going in our road system. going to Delhi, there are 4 lanes. If it is a single lane, it is single mode. If there are 4 lanes, it is a multi mode.
तो फिर हम मल्टी मोड को पॉइंट टू पॉइंट तो नहीं कहेंगे, फिर तो 4
रोड तो दिल्ली पहुंच रहा है, but the point to point link between user and the destination, that is point to point link. Now point to point link, how to achieve that? It may be a single road, it may be a multi road, single lane, multi lane. So when you are on multi lane, you have to be very very careful within the lane, नहीं तो बाकी से टकरा जाओगे. If there is a one vehicle और सिंगल रोड, आप अकेले ही जा रहे हो तो कोई चिंता नहीं है, यू कैन मूव. सो प्रॉब्लम इन मल्टी मोड एंड सिंगल मोड डिफरेंस इज डिस्पर्सन. मल्टी मोड इज ए पैरेलल कम्युनिकेशन, सिंगल मोड इज ए सीरियल कम्युनिकेशन. सिंगल मोड कैन नॉट कैरी मोर पावर, मल्टी मोड कैन कैरी मोर पावर, बट मोर डिस्पर्सन. Single mode means number of modes are there. If you go in the electromagnetic theory, thousand or few thousand of mode travel in the optical fiber. When you talk about multi-mode fiber, maybe around normal dimension, if it is a 50 micron power operating at 850 nanometer, so you will get number of modes, maybe around 3000 modes are traveling. Yeah, it is given by B number. B number is 2 pi over lambda A numerical aperture. So what is wavelength? What is the size of the fiber? What is the numerical aperture? And modes, it is given by B square over 2. So you calculate the B number, from where you can calculate the mode. For single mode fiber, B number should be less than 2.405. So multi-mode has only benefit if you want more power. But lot of dispersion is there. If you are to go at the high data rate, you have to use the single mode fiber. Mbps is okay with the multi-mode fiber, but Gbps is not possible with the multi-mode fiber. Maximum 10 Mbps or 100 Mbps. Then we have to go for the single mode fiber. Data rate is for the single mode. Okay. If not clear, you can come to my room, then we can discuss. So single mode means, see, you have an optical source. Number of a long beam is coming. Now you will put some pinhole aperture between the beam. So rest of the light will cut off.
How many people can communicate at one time with single mode fiber?
It is not with the fiber. It is the multiplexing. How many users you can multiplex? Single mode fiber इसमें तो power travel करेगी. जो आप power it will be a mixed signal, modulated or multiplex signal. Now it depends upon your multiplexer. Okay. So number of user will depend upon how you multiplex. Fiber, it will travel. Even number of wavelength can be put over the fiber, because each wavelength is different.
So how number of wavelengths can we put? Because we are saying that we operate at 1310 nanometer wavelength. So it is a particular wavelength, and how we can use number of wavelengths?
Is 1310 means 1310? It can be 1305 to 1315.
So but we say now operating wavelength is 1310.
That is the central wavelength. When we say 1550, we call it the wavelength division multiplexing. आप frequency division multiplexing पढ़ते हैं. So number of frequency can be multiplexed. Similarly, number of wavelengths can be multiplexed. But these wavelengths should be different. Difference may be 0.1, difference may be 0.01, which we call as the DWDM. But they should be different. Each path is different. You know the wavelength and frequency relationship. So 1550 and 1550.1, they are different. So now when you are talking about terabits of data, this difference is 0.01. So it is possible. कैसे?
फास्ट मतलब हाँ हाँ नहीं आप इट इज द डाटा रेट। जब आप स्पीड की बात करते हैं आप डाटा रेट की बात करते हैं। डाटा रेट इज नंबर ऑफ पल्सेस इन 1 सेकंड, kbps या mbps। फाइबर इज ट्रांसपेरेंट टू डाटा टाइप। सिंगल मोड पर डाल दीजिए, मल्टी मोड पर डाल दीजिए। जब आपने डाटा रेट देखना है, आपने देखना है पल्स ब्रॉडन कितनी हुई है। in multi-mode fiber there are two type of dispersions: intermodal dispersion, intramodal dispersion. But in single mode fiber only intramodal dispersion. Intermodal dispersion will not be there, and they differ by a factor of 1000. Intramodal is of the order of nanosecond. Intermodal. In multi-mode fiber the dispersion is of the order of nanoseconds. In single mode fiber dispersion is of the order of picoseconds. 1000 का डिफरेंस है तो 1000 से डाटा रेट डिफर कर जाएगा। इट इज द डिस्पर्शन विच इज इंपॉर्टेंट। अदरवाइज मल्टी एट सम प्लेसेस मल्टी मोड फाइबर इज इक्वली गुड। यू नो इन द मल्टी मोड फाइबर वी हैव टू टाइप: स्टेप इंडेक्स and gradient index. The gradient index fiber is only to reduce the dispersion, no other difference. Dispersion is reduced by factor of 100. So dispersion is important, size is not important. Okay. So now you know that in a link you have a number of problems, number of variations. We need different test equipments. So they may be what you call as the optical power meters or continuity testers, visual fault locator, talk set, spectrum analyzer, OTDR, BER tester. All number of components are required. You see, these are all power meters. So you can measure power at any point. You can just take out the terminator and measure how much power is there. So first point is to check the power. So you need the power meter, and here this power meter is a optical power meter. You need continuity tester. Continuity to check the continuity of the fiber from one end to other end. And you know fiber is a dielectric. You can only send the light from one end. If it is reaching at the other end, it is a continuous power. So you have to launch power. These are all continuity testers. You send the power from one end, check at the other end. Patch cords, all other parts. Because initially they are in the real form. So you can check very easily whether it is continuous or not continuous. So some components are required. Then you need optical spectrum analyzer. Mostly it is required when you are talking about the multi wavelengths. Single wavelength में एक ही peak होगी आपकी. But in the multi wavelength, you see 4 wavelengths. They should be well separated. So like you have a spectrum analyzer for electrical signal. Similarly, spectrum analyzer for optical signal. This is your start signal. You will get this type of signal at the end. All broadened. Lot of noise. So you have to check the signal. You have to correct the signal. Lot of corrections, filters, your error corrections are required. So optical spectrum analyzer, then BER tester. So BER tester is not just like a meter. You connect the fiber, you will get values 9.7 into 10 power minus 8. Whatever the parameter is, it is a standard unit like your DSO, but very very expensive. It may cost around 12 to 15 lakhs. So BER tester, then of course we need the OTDR. OTDR is not only to test the quality of data, but to check the fault in the fiber. There may be break in the fiber because your fiber is all underground. आपने देखा होगा fiber laying. They have a channel. They put the PVC pipe. They put the fiber. So if you have to check it, it is very difficult, and it is a long link. So you send from OTDR, you send a signal from one end, and signal travel, and it will, if there is any break, it will come back. It is just like a echo method. Signal go, it will come back. You know what is the speed of light? You can measure the time, start and receive. So you can calculate. You know the refractive index of fiber. you can calculate where is the break. So OTDR is very, very important and indispensable component in OFC. So different variety of OTDR are available, starting from maybe some 40,000 to it may go up to few lakhs, 4 lakh, 5 lakh, 10 lakh, depending upon type of OTDR, depending upon features, depending upon range. Some OTDR may cover only 10 kilometer, it may go 100 kilometer, it may go 500 kilometer also. So you need more powerful source. That will decide the cost. So then we have to look for testing. Testing again, we go for two variant testing. One is the attenuation, other is the dispersion. You know, in attenuation, the amplitude will fall. So power is related to amplitude. In dispersion, the pulse will overlap. What you call as the interference, ISI, intersymbol interference. So it should not be like this. It should be this signal. So broadening. So I cannot separate this. So this will decide data rate. What is the possible data rate? So both attenuation as well as dispersion, they affect the system. Attenuation, it will decide how long link is possible, how much link length is possible. Data dispersion, how much data rate is possible. Your system may not be operational at 10 Gbps, but it can operate at 1 Gbps or Mbps. One have to decide either to go for the better component or to operate at the desired data rate, because you want the signal. Your internet speed is not same all the time. Variations are always there and we accept those variations. But system should be operational. Link तो होना ही चाहिए. Okay. So to measure this, we go for the bit error rate, BER. So we go for, now there are different means. We go for the, what is the eye diagram. Eye diagram is the first test. Even in our normal life, सबसे पहले हम आंख देखते हैं, आंख खुली है या बंद है. खुली है तो ठीक है, बंद है तो जय श्री राम. ओके, उसके बाद then we go for the further analysis. One is the eye diagram, eye testing, eye opening. तो कई बार आधी सी आंख खुली होती है, जब थोड़ी थोड़ी बंद हो रही होती है, तो we go for the further analysis, or we call the doctor. That is the next part. So eye diagram is the first attempt. It is just like first aid. So then we go for, from eye diagram we draw the bit error rate. We draw the histograms. We go for the analysis. We draw the histogram. From histogram we calculate what is the standard deviation, all those parameters. Ultimately we go for the BER rate measurement. Now either you go for bit error rate meter. You spend 10 or 12 lakhs, or you go for the economical system. कल हमारे चीफ गेस्ट जुगाड़ की बात कर रहे थे, तो go for the जुगाड़ in the lab, because you have so many instrument in the lab. आपके पास oscilloscope है, आपके पास सिस्टम तो है ही है, because you have the OFC system जो आप चेक कर रहे हो, और oscilloscope चाहिए आपको. Computers are now available. Earlier computers were not there. Now so many softwares are available. So we can go for this bit error rate. I already mentioned it is defined as the ratio of number of errors in a given time to number of bits in that time. So NE over NT, errors over time. So normally in many applications BER is of the order of -9 or maybe varies depending upon system to system. In Wi-Fi even 10 to power 5 or 10 to power 6 is acceptable, but point to point link better. If you talk on your mobile or if you talk on your landline, lot of difference you will find. Landline में no atmospheric interference. So but as per ITU standard, a OFC system, the BER should fall between 10 to power -9 to 10 to power -12, or -12 to -9. -12 is much better, and -9. So within this range it should be there. So BER is a parameter of measurements. So mostly we either we go for the instrument or we measure bit error rate by using the statistical likelihood. Now it depends. There is a statistics. Your signal may or may not be affected. There may be rain in Chandigarh or not in Delhi. You are covering up long distance. So your signal may be affected at a particular place or not. So it is always a statistical in nature. We have to go for statistical analysis. So can be measured empirically, and there are many factors which affect the BERA. The major factor is signal to noise ratio. So how much is the noise? Oh, it may cover all type of noise. And signal is your power. So power to noise ratio. And in many cases we maintain that signal to noise ratio should be 14 or 15 or 18. More it is, better it is. More the signal to noise ratio, lesser is the noise. So we measure mostly this part. So BER, the main factor I mentioned which affect, one is the inter-symbol interference, which affect the quality of data. We measure by the non-zero extinction ratio. Anybody know about this ratio? So we are talking about 0 and 1 signal. When the signal is 0, power should be 0. When the signal is 1, power should be more. So what is the ratio of power when signal is 1 and when signal is 0? Ideal, it should be very, very large, because 1 large, 0 small. But it is not like that. Your detector, your source, there is always a dark noise, thermal noise, short noise, different type of noises are there. So it will not be 0, but it should be as large as possible. Or it may be opposite. In some books, you may find power when signal is 0 or power when signal is 1. In that case, it should be very, very small. Then pulse position jitter. Jitter क्या होता है? जोर से बोलिए, ठीक बोल रहे हैं? Okay, you may call in this time. It is on basically on the time axis, because you are measuring the signal at a particular time. If there is a variation in this, that is called the jitter. So you put some reference. So any variation in the reference signal, that is called the jitter. अगर आपका reference ही vary कर रहा है, तो output vary करे. So jitter should be as small as possible. But it is again there. Whenever you have a pulse on the oscilloscope, what is there? You have time axis, you have voltage axis. So any variation on the time axis, jitter. Any variation on y-axis, noise. So we measure all these parameters. So BER estimation can be done in this fashion. So BER, I mentioned the BER tester, or now you check what you call it the semi-quantitatively or qualitatively, or what you call the pseudo-quantitative manner. Now you can take the help of software. You draw the eye diagram. Now eye diagram, you are, in this case you need a digital storage oscilloscope, DSO. Now DSO can be connected to computer very easily. All they have the connectivity. Earlier they were having RS-232 connectivity, now USB connectivity is there. Fast. Now you can transfer the data from DSO to computer, and on the computer now you have the Q factor analysis softwares. Different company like your Agilent, they provide this, but it is a dedicated software for particular companies. So you can have this software. The cost may not cost, it will not cost more than maybe 1.5 or 2 lakhs. So from 12 lakhs now you are coming to this much value. So but here it is a semi-empirical method. We call first eye diagram. So this BER is measured on the what is called the threshold detection. So you have a threshold. If signal is below threshold, it is 0. If it is above threshold, it is 1. So threshold detection part is there. So we measure the probabilities. I mentioned it is statistical analysis. So we talk about the probabilities. Now you have a threshold level. This is the threshold level. If signal is below this level, it is 0. If signal is above this level, it is 1. But there are always variation. The noise in 0, noise in 1. So This is the voltage axis. So one signal, the reference value is this one, but if there is variation, the variation may be both plus minus. So one signal may come below the threshold. This is the threshold level. It can come down. So this shaded, this crossed area, this is the probability of error in 1. Similarly, 0 signal will go above. So this shaded area, it is the probability of error in 0. So you can measure what is the probability in 0, what is the probability in 1. But whether it is error in 0 or error in 1, both are error. So we measure the probabilities. P0 may be B threshold to infinity. Why infinity? Because it will rise. It will go from threshold to higher value. For one signal, it will go from threshold to minus infinity, lower side. So you add the two values. You calculate the probability. In mathematics, all error analysis, all part is there. So one can calculate it. This is the power and integration. Then you calculate BR is total probability. So A P0 plus B P1. So these one know the probability. Now these probability they are. This is what I mentioned earlier. Threshold. So you send 1010 signal. Now at the receiver you get 1 is okay, 0 is okay. Now this 1 has come down. This will be detected as 0. Now 0 had gone up. It will be detected as 1. So your receiver will get the erroneous signal. You send 1010, it is 1001. Lot of change. So one have to look for this. So now this probability is related to what we call as the Q factor or BER. There is a error theory, and in that case you can see the probability is related to this is error function. Probability is related to Q. And Q is nothing, it is B threshold minus B0 over sigma 0. This is the difference in 0 signal threshold or 0 signal over standard deviation. So you have a probability, you know the standard deviation, sigma parameter. So one can calculate it. So if you plot the probability and Q factor, you will get this type of curve. This is just like a waterfall curve. Why we generally you will find the Q factor. So why Q factor? Because Q factor is a number. It is easier to deal with a number. Probability is 10 to power minus 9, minus 12, minus 14, minus 15. Difficult to even write or pronounce also. But Q factor, if you want say BER minus 9 is here. Q factor is 6. Minus 12 is here. Q factor is 7. So if you talk about the BER, it should be 10 to power minus 9 to 10 to power minus 12. But Q factor 6 to 7. The Q factor should be between 6 to 7. So either it may be Q factor or it is BER rate. It is the one and the same thing. Okay. So ultimately we see now another factor is small variation in Q give large variation in the signal. You can see this part. Variation from 7 to 6 to 7, one variation. Magnitude 1. But here magnitude 1000. 10 to power minus 3. So both can be there. So we go for the eye. This is the eye diagram setup. Simple. This is a diagram for Keyser's book. So you will see link is there. In the lab we have the kits. Optical transmitter, optical receiver, fiber cable. Now what is required? You need a digital data module. We call it PRBS. Pseudo random bit stream. It will generate random pulses 010101. Now these pulses they are you need the DSO. So you have there is a vertical signal, there is a trigger on the oscilloscope. Two signals. So trigger, now here you have a again time signal and data signal. Data signal is given to system. Trigger timing signal goes to trigger of the oscilloscope. And then output of your link is connected to another channel of oscilloscope. So you can have the link, and this is but the system in our lab. So this is a OFC link kit. This is a pseudo random bit stream. This is a DSO. Now through computer it goes to monitor. So you get the histograms. These are the histograms you can see. And if when now you have to sample the data. You have to take samples, maybe 1000 samples or more samples. More the number of sample, better is the accuracy. In all statistical analysis, more is the data, better is the accuracy. Same is happened here. So you can collect the data, eye diagram, then you can draw the BER. So this is what eye diagram you will see. So you see here it is quite broad, well open. Now here it is goes on closing toward. So this is after 2 kilometer, this is after 6 kilometer. Because your attenuation and dispersion, they are function of distance. जैसे distance बढ़ता जाएगा, loss आपके increase करते जाएंगे. So your signal may be very good at 2 kilometer, but it is not good at 6 kilometer. So you have to look. But here you see there is some closing, eye closing. So now check what is the Q factor here, what is the BER rate, because it is mentioned. Here the BER rate will be very, very high, maybe 10 to the power minus 50 or 10 to the power minus 100. If the BER rate is more than 10 to the power minus 12, we need not to bother, because system is good. When it comes below 10 to the power minus 9, then we have to be concerned. So this is what you call about the eye pattern. I mentioned this is the jitter, broadening on the y-axis. This is the noise. Okay, so all these you see, this is the eye diagram. From here you can calculate how much the jitter on the oscilloscope. You can put the two cursors at this position and at this point. You can measure how much is the jitter. You can measure the noise level in 1. This is the RMS noise in 1. This is the RMS noise in 0. You can measure by the 20% rise time. So pulse at 20%, pulse at 80%. You can measure. It is 60%. But in both standard book, you will find the 80%. You can multiply it by 1.33, because practically it is not possible to measure 80%. Because at the top of the pulse, lot of noise will be there. At the bottom of pulse, lot of noise will be there. If you perform the measurement at that point, it will be noisy. So we go at 20% and 80%. This will be more clean. 60% multiplied by 1.33 to compare the two. So always measure by the 80% rise time or 80% pulse width. Pulse width is again from, you can have it at 80% level. So one compare with the standard. So eye diagram, you will get all these factors. So all these factors, jitter, noise, they will provide us the information about the quality of the signal. So sometimes we also you may come across the term what is the power penalty. Penalty लगेगी, late fees जमा कराओगे, you will get the fine. Penalty. This is also a penalty. If your signal is broadened, what will happen? Amplitude will come down. Amplitude come down means power has come down. To maintain the amplitude, you have to increase the power, and this is called penalty. So this increase in power may be by any mean. So we call it power penalty because of dispersion, power penalty because of extinction ratio, power penalty because of certain other effect. So this is penalty. So you get, ultimately you will get this type of eye diagram. If you have a very good quality of signal, you will get this type of eye diagram. Very fine. If there is a noise, you will see there is noise in the signal. If there is a dispersion on the time axis, you will get jitter part. Jitter part will tell you there is a problem on the time axis, transmission of the pulses, or maybe non-synchronization. And if both are present, you will get eye closing. Very poor quality of eye. So it will tell you the quality of the data. And I mentioned already eye diagram. So you get this. It is a qualitative means of measurement, or you may call it as a semi-quantitative. If eye is okay, no need to proceed further. If there is a problem with the eye, then we have to further analyze how much is the problem, what is the bit error rate, or what is the Q factor. Then we have to go for the Q factor software. We have a Q factor analysis software. It is available in our OFC laboratory. We regularly use it. So now your DSO will be connected to your computer, and now you need the software, Q factor analysis software. So it is what you call as the sampling. So sample, how many sampling is required? More the sample, better is the result. Your oscilloscope, there is a one parameter. एक तो bandwidth होती है 60 megahertz, 100 megahertz. Other is the sampling rate. 50 mega samples per second, 1 giga sample per second, 10 giga sample per second. So this will decide about the sampling rate. Fast. So we go for the, now if the data go to this factor, it will generate the histograms. So from the histograms you can see this is a good data, this is a poor data. And then once the height of this histogram, it will tell you how many samples are collected. So generally we go for minimum 1000 samples. It will take 2 to 3 minutes depending upon sampling rate of the oscilloscope. So once it is there, eye diagram is okay. Qualitatively you can check. Otherwise, on the software you will find some window will glow. So analyze button, it will be activated, and you will get this diagram. So this is a full short view of the screen. So you have to check connectivity, RS232 connectivity. Number of in which communication port oscilloscope is connected. You have to check number of samples, set 1000 or 100 or 10,000 or 1 million. It is your choice. Error is always square root of number of samples. So then the analyze, you will get all these values. Now one is the RMS noise in signal 1, RMS noise in signal 0. This is level of signal 1, level of signal 0. This is threshold level, Q factor 6.9, BER 10 to the power 2.6, 10 to the power minus 12. So it costs not more than 2 lakhs. Of course, your system is different part. So regularly one can monitor. And in all your telephone exchange or those unit, this unit is always there. The continuous monitoring part is there. So these are the factors which affect the BER. If BER is not good, you have to check. So the major factor is, you see, what is the input power and what is the signal to noise ratio. Because power has to be optimized. It cannot be more, it cannot be less. If it is less, lot of noise will be there. Signal is less. If it is more, non-linear effects will be there. Different type of non-linear effects are there. Raman effect, Brillouin effect, cell phase modulation, 4-factor, 4-way mixing. Number of factors are there. Maybe come across when you further go in this subject. So one have to look for. You have to optimize the power. It is not that any power can be launched. We have to avoid the non-linear effect. We want the linear system. So optimization of these is very, very important. So many part in research we have to go for optimization. So similarly, signal to noise ratio. More the signal to noise ratio, lesser is the probability of error. So one have to maintain certain signal to noise ratio, certain power, certain signal to noise ratio. So again I mentioned you have to maintain the system. Signal maintenance or device performance. So number of problems will be there at the transmitter, at the connector, at the amplifier and other part. So you started with this type of signal. In between travel in the optical fiber, lot of deterioration, amplitude, dispersion. Then you have to correct it. What you call the path engineering. You have to maintain the system. You have to go for the amplification. You have to go for the regeneration of the signal. Regenerator. It will go for reshaping, retiming and repeating. Repeating is the amplification. If you have a repeater, it is only amplification. If you have a regenerator, all three R's. So ultimately you should get same signal. Okay. So we have to look for what is called the path engineering. All things have to be maintained. You have to look for the signal, fiber, degradation in the optical fiber, amplifier, all part has to be checked, and if you get this type of signal, it is not the desired signal. Lot of broadening, lot of signal to noise. Yellow is the noise, other is the signal. You will not get the desired signal to ratio, and you have to correct it. One have to go, but it's called the, generally we call it the repeater. If the power has come down, you can use the amplifier. At different distance, whenever you go along any optical link or even in the cable connection, you will find some amplifier. So after certain distance, one can put the amplifier where the power go beyond certain limit. So one is the amplifier, other is the dispersion. Now in the dispersion, we go for the correction of the pulse timings. What you may call it as the compression of the pulses. They have broadened, now you have to compress or you have to compensate it. So we can use the amplifiers, but here we need the optical amplifier. लगता है आपका सेशन हो गया ऑप्टिकल एम्पलीफायर का, मिस्टर तिवारी, he covered it? नहीं, CSIU से आए नहीं सर, इन्होंने अटेंड नहीं किया. Okay. So earlier what was the problem? Optical amplifiers were not available. Here somewhere you must have read EDFA. It is erbium doped amplifier. It is an optical amplifier. Optical amplifier means you have an optical signal, it will pass through the amplifier, it will be amplified, then it will be travel. But before 90s, optical amplifiers were not available in particular window. Otherwise, laser is an optical amplifier. Laser came in 60, but that laser was at different wavelength. You need an amplifier at 1550 nanometer, at 1310 nanometer. It is a material dependent. All lasers are material dependent. So earlier what was the process? You have an optical signal, convert this signal into electrical signal, use the electronic amplifier, amplify it, again convert electronic signal to optical signal. So it was a bottleneck in the system. When you convert from optical to electrical, some loss is there. It is never 100%. When you amplify it, amplifier, it has own noise. It will add noise to it. When again you convert optical to electrical to optical, again conversion is not 100%. So it was a big problem before 1980s. EDFA, it changed a lot. But EDFA optical amplifier, it is only available in 1550 window. That's why 1550 window is more attractive. I don't know whether you have gone through this system, this part. If you have a conventional single mode fiber, silica fiber, here attenuation is minimum at 1550 nanometer and dispersion is minimum at 1310 nanometer. At 1310 nanometer, attenuation is more. At 1550, attenuation is minimum, but dispersion is more. So you cannot have both parameters at the same time. So as a result, if you go for the look for 1310, it can carry high data rate because dispersion is less. If you go to high distance, you can go for 1550 nanometer. So optical amplifiers are required. Now if there is for power, you can go for optical amplifier. For dispersion, you have to go for the compression. So either you can use the electronic type of system, because electronic systems are not as fast as the optical system. Speed of light, photon can travel fastest. So we want everything all optical. So now they come out with a fiber which we call as the dispersion compensating fiber. This is a fiber with negative dispersion. If the pulse will travel in this fiber, it will be compressed. So positive dispersion, it will broaden. Negative dispersion, it will fall. Now DCF is a routine feature. large negative dispersion coefficient. So maybe after 100 kilometer you can have 10 kilometer DCF or 5 kilometer DCF. This will give the solution. Okay, so all these corrections are there. We have to go for what is the dispersion or power maps. So you have to maintain how much is the power. Regular features are there. So this is the power map. So you see, this is the optical power. So you started with this power, it will come down after certain distance. Then you put the amplifier. This is the amplifier. The power will increase. Then it travel in the optical fiber, it will again decrease. So after certain distance, you have to put the amplifier. After certain distance, you have to put the DCF. Now mostly they are put in combination. So you have the DCF and amplifier DCF. This is called pre-compensation. Before sending the signal, you just maintain it. You increase the amplitude. Then at the end it will come. Or you can have dispersion. You know, when you have dispersion, this is the DCF. In the DCF, it will come down. When it will travel in single mode fiber, it will increase. So here it will come down. Then it will travel in this fiber, it will increase. Again it will reach here. So come down. So this is pre-compensation. This is post-compensation. कुछ लोग पहले से ही प्रिकॉशन ले लेते हैं, मलेरिया की गोली पहले खा लो, but after the effect. So this is post-compensation. So it depends decision of a particular system, particular service provider, whether to use the pre-compensation or post-compensation. There is not much difference in both the two. So this approach one have to follow. So this is the total long, any typical long haul link. You have to maintain it. So terminal equipment, fiber, amplifier, regenerator. After few number of amplifier, you have to add regenerator because each amplifier will add noise. So after certain distance, again your data pulse has to be refreshed, retiming, reshaping, all part they have to be kept. So after maybe 4 or 5 amplifiers, you use the regenerators and again. So this is how the link is maintained. Now all over the globe, all countries now they are internationally connected by optical fiber. Earlier we used the satellites and now it is the optical fiber. The distance from say India to US is around 20,000 kilometers. If you go for the terrestrial distance, but from satellite, how much is the distance? 72,000 kilometers. Pulse will go up, uplink, downlink. So whether it is a Singapore or it is a US, signal has to travel 72,000 kilometers. If you calculate the speed of light, the time, how much time it will take, it will come out maybe few milliseconds, 100 milliseconds or in that range. But if you calculate for 16,000 kilometers, it will come very, very small, microseconds. So earlier, if you talk any person in US, आपको एक matching करनी पड़ती, but now it is not there because distance has reduced. There is no signal delay. So all these parts one have to. So now it is preferred that it should be a point-to-point. Fiber is laid over the globe. You say maybe around 2,000 miles per hour. This is the rate how much power is laid. All now they are connected by optical fiber. So high capacity link one have to maintain maybe by amplifiers, by dispersion compensating fiber or other parts. You may need different filters, different type of error correction, gain correction. So many components are required because you need a high, good quality signal at the output. So it is not only the optical source, receiver and optical fiber, many other components are equally important for OFC. So for maintaining, now it is not only the point-to-point link, but the unique feature of OFC is the wavelength division multiplexing. WDM or DWDM, dense wavelength division multiplexing. You can send maybe 55 wavelength or nowadays even more than 200 wavelengths. Why go for WDM? The point is to use the potential of optical fiber. When you go for optical fiber, we talk about the infinite bandwidth. But our data is not that much. We have to multiplex it. So if you need large capacity data, either you use the high data rate. High data rate means you need very narrow pulse, very fast electronics. This is not possible. On the other hand, you use the number of channels. Now on the optical fiber, if you go data rate beyond 1 Gbps, there are large nonlinear effects. System will not operate. Now nowadays it is the time for 100 Gbps. 40 Gbps is common. Now 100 Gbps is in the testing stage. Now 100 Gbps cannot be put over the single mode fiber. Lot of interference will be there. So what is the approach? You use the number of channels, lane system, 4 lanes, 6 lanes, 8 lanes. On single lane, you work at 1 Gbps. Put the 100 lanes, 100 Gbps. So this is the technology of multi. This is just providing the expressway to any destination. So all this has to be maintained by in the optical link. Some signal had to be monitored all the time. All the maintenance parts are there. So system engineers are there. If you go in any of the service provider or BSNL or other company, they have number of sections. One is the marketing section, other is the transmission section, other is the field section. Their job is, responsibility is to particular section. So this is how we operate, design or analyze the system. So this part, analysis part, is very important if you have to provide right quality of data to the users. So I stop here. In case you have any other query or any question, you are most welcome. From our नोडल सेंटर किसी से देख लीजिए. गवर्नमेंट इंजीनियरिंग कॉलेज भरतपुर. You have any query or any question?
No sir. No sir.
You are fine?
Yes sir.
Okay. So thank you. I will move to the next center.
Thank you very much.
Balaji Group of
No question, sir.
You have any query?
No query, sir. Thank you very much.
Okay, thank you. Delhi? Dr. Ambedkar Institute. Do you have any query or any question? इनका लगता कुछ ऐसे ही है. Go to the next center. Do you have any query or any question? You can ask, please. Rajkumar Goyal Institute. In case you have any query. Any query from your side? Your audio is not clear here. Northern India Institute.
No query, sir. Thank you.
Do you have any query?
No, sir. Thank you.
So thank you very much, all the knowledge centers and all the participants in the studio. I hope I try to give you the input related to these parameters. And in case students you have any queries, you can interact with me anytime in my office or in my lab. Okay. So
we will have a tea break for 20 minutes.
Now we will have a tea break for 20 minutes and we will start at 11:45. Okay.
बोल दो सर उनसे। Please speak.
Excuse me, sir. Sir, you are not audible for us in Bharatpur. Hello. Yeah. Fine, sir. Huh?
Hello, sir. At Bharatpur, am I audible now?
Yeah, you are audible now, sir.
Okay, okay, sir. Now, can we start now?
Yes, sir.
Okay, sir. So, again, I look forward to the installation process again. I will repeat the checklist. Firstly, we are looking at the equipment's requirement side. Now, as I told you earlier that equipments are different for the different installation process. Like if we are digging inside a city, we require only a man force. So there will be a different equipments needed at that time. And in the similar place, some team is planning an optical fiber installation nearby a mountain or on the mountain. So again, the equipments list will be changing over there. We require a very heavy machinery over there, even some of the TNT also over there to bombard the mountains, some of the mountains to clear the way for the optical fibers. And sometimes there is even more heavy machinery to be used for installation when we are placing an optical fiber inside a sea. So again, we have to look all the requirements to be made for the installation, and it should be done before the installation process only. Because after looking, if we are just planning for installation underwater and we having the equipments of the laying an optical fiber on a road, so it's not possible for us again to place an optical fiber under the sea. So we have to prepare a checklist for all the equipments we required for a particular task. Then we have the documentation ready for installation. Now documentation, again I said as earlier that documentation is very much important for planning of an optical fiber. Before even starting the equipment list, we have to do the documentations, because if we are planning to you can say dig into a city, and we have to place all the optical fiber underground through a city from one point to another. So it's very important to take permissions from the nearby commissioner's office, or you can see the PW department also. So only then we will be able to dig all the city, because it's not very usually you can just go over there and start digging and stop all the roads over there. So you have to take particular permissions for particular things to do in the city, as well as if you are going from one country to another, if you're laying an optical fiber in undersea. So it's very important you take the international permissions also from both the countries, that they are allowing you to pass the optical fiber from this point to this point at particular this point you will be working. So it's very important to take the permissions from all the governing bodies. Then we have a link tour with contractor. Like this, I told you that if Airtel, Vodafone, or any other company is trying to place an optical fiber through the city for their services, so it's not that thing that they will send their own engineers to do the linking of the optical fiber. They actually will be placing in contract to the people who are already working into this domain. So because they're already having all that equipments to be used for that, so it's very easy for them. Again, they will find a route map. They will locate a map that from you can say from Delhi to Chandigarh they have to place an optical fiber. So there will be a contractor over there, and he will be telling all the you can say all the aspects we can use for an optical fiber laying. As we have from Delhi to Chandigarh, we have a national highway. So from national highway we can use all the optical fiber in the pole to pole passing by, and whenever we are entering a city, we'll dig it underground. So there will be a link route. They will decide a route where they have to dig all the optical fiber. Likewise, we have to do the link route tour inside. You can go for the mountains or for the undersea. So there are different kinds of link tour also. Also, we are not deciding at a particular point. We are not only deciding a particular one route only. We are going for different routes at that time. So so we have to look different kinds of routes also. Then afterwards we come for the safety rules reviewed with the contractor. Again, it's very important to look at that we have to ensure about all the safety procedures, like we are using an optical fiber which is very you can say harmful for the engineers working over there, because if it's broken from one side, so it's very difficult for one to recover from that position. So it's very important again. So like that only, all the contractors have to make a safety rules for contract reviewed with the person who is actually claiming for all the optical fiber installation. Then we having a test plan reviewed with contractor, end-to-end loss testing. So again, it's very important if you are planning a route from one point to another. It's very important that you do the end-to-end loss, because the most important thing in optical fiber that we should not have much losses, because already we are into the losses of near about 2.05 dB per kilometers. So we have to plan all the end-to-end losses which will be bearing through, and according to it we will be using the power sources over there across the optical fiber. So it's a very important checklist we have to done before the installation of an optical fiber. Then we come across and the installation requirements, or you can say the general guidelines we have to go through while installation of an optical fiber. Like first of all, it is the handling of an optical fiber cables. Again, before I tell you that handling an optical fiber, it's very sensitive, so we cannot just handle it very roughly or very carelessly. So it's very important to use proper procedures to handle an optical fiber reel or a drum, or you can say a simple optical fibers. So the first point we have to look at, how did they handle the reel of optical fiber with very care. So it's not that thing that if an optical fiber is inside a reel, it's you can handle it very easily, or you can just roll down on the roots. So again, it is very important for you to just take care of the reels of an optical fiber, because the optical fiber can loosen up inside the reel also. Then we have move small lightweight spools of optical fiber cable by hand. So again, if you are having a very light spools of an optical fiber, you should just carry with your hands properly and place them accordingly in the horizontal direction. Do not put into the vertical, as I told you a day before yesterday. We should only use a particular proper set of instructions to handle all the optical fiber reels. Then we have the cable reels shall be removed carefully to avoid the damage to the cable. Now again, it's very important that you remove all the optical fiber from the cable. If you are not removing it, because there is some procedures you have to follow to take out all the optical fiber from a reel. I'll show you a diagram over here that how you have to take out all the optical fiber. If you're having a reel, we generally use a support structure, which is actually like this. and we put a reel over here for the optical fiber. So this is how we place optical fiber at the construction site. Then again, it's not like that you just start pulling down all the optical fiber. There is a process that you have to always take out the optical fiber from the top of the reel. You cannot just take it out from the bottom of the reel, because how much pressure you will be allowing at the reel, it will be taking out more and more optical fiber at a single time. So it's very important you always take out the end from the top of the reel. So it's very easy how much pressure you will be applying, only that much of the optical fiber will be coming out of the reel. So again, it's very important to look out for all the procedures and the steps to be carried out at the installation process. Then we are having the installation requirements, then the support structures, as I already shown you over here. These kind of support structures are already used at the time of constructions, because you cannot just disassemble all the optical fiber from the reel very easily, or just lay down the all of the ground. So it's very important you always have a support structures at the construction site, so that they can support all types of reels over there and all type of weight of an optical fiber. And it's very important again that I already told you, if a company is laying an optical fiber and they have already laid that optical fiber over there once before 5 to 6 years back, and they are trying to lay in another optical fiber for another services, so they should take care that they are already having an optical fiber over there in a particular conduit. Conduit, I told you in the components part that it's a fiber material over present to give an extra cost to them. So I'm sorry for the disturbance right now. So we continue this, that we have an optical fiber inside a conduit over here. So it's not easy for a particular company to just replace all the conduit for a particular optical fiber. We do not have to use the same conduit for the particular another fiber over there. So we have to place another conduit into it, and we have to place another optical fiber through that conduit. Then installation process, there are different kinds of installation process right now we are going through. Like first we are looking for an indoor installation process. Indoors, we are having different kinds of indoors installations also, because we are not only installing the optical fiber throughout the cities only, we are having particular types of optical fiber we are laying inside the companies, we are laying inside the construction zones. So we have different kinds of procedures again there. The first of all we are using in the cable, in the indoor cabling, is the cable trays. We are actually using a cable trays over there. We are using the jacks over there to put optical fiber throughout the ceiling or throughout the your roofs. Then we have it in the hangers. Hangers, again, it similarly works like a hangers we used to for the clothes also. We place a particular angles at particular distance only. Then we place all the optical fiber through them. Then we having another process also, that is outdoors. Outdoors, we are going with the direct buried, means we are just digging all the ground over there, and we're just putting all the optical fiber there. And then we have a plowed or blown into conduit. Plowed or blown into conduit is again a simple process. We use a machinery over there which actually take all the optical fiber blown into a conduit automatically. We do not use any man force over there to put all the optical fiber through conduit. Then we are having a very simple process, again an area between poles. Again, it's a very easy process. We do not have to bury the optical fiber, or we do not have to use any kind of machinery. What we do is that we take the poles of electricity. It can be electricity pole or a simple pole at a particular distance. So what we do is we take the optical fiber from one end to the another pole, and it will be hanged inside the inner. So from at this point we should be very careful that the distance between two poles should not be very greater, so that it should not lead down at a particular point. So it can causes a type of losses, a bending losses inside an optical fiber. So you should be very careful about the bending of the optical fiber at the aerial poles. Then again, the installation guidelines, which is very important. You do not have to twist any kind of optical fiber at any point, because twisting an optical fiber can break the glasses inside, or maybe you can have particular losses from one point. So it will be very difficult for us to find a particular loss at that moment. So we should be very careful about the twisting of a cable at any point or any circumstances. Then we are talking about the indoor cabling. Indoor cabling, we have I'll show you an image of an indoor cabling like this only. We are having a hangers like this. We are using hangers and different types of hangers in the cabling of an optical fiber. So it's very important to again use a hanger at a very you can say a specify hangers for specify optical fiber to handle it. Then we having some of the hangers like this also in the J shape or J hooks. So again, it's very important to look all the optical fiber weight and the distance between the hangers. Then we are using these kind of trays over the roofs. Newly designed buildings are actually trying to use the trays because it's very useful, and you are able to hide all the optical fiber inside an installation process. So again, it's a very important thing if you are doing inside a building also. Then we talk about the outdoor, how we use the process, the outdoor burying of an optical fiber. This is an image showing you the outdoor cabling. This is how we exactly do. We using different kinds of method also. One method is called as trenching. Now, trenching is a process of making a very minute digging inside inside a door. You can say besides the road or on the road. It's very important because you cannot dig a big holes over there, which can be very harmful for other people who passing by from there. So, using that machine, it's very possible to actually make a hole of micron meters also. So we are using that kind of machines over there for the digging of an optical fiber. Then again, we are using the same process at the side of the railway stations also, or at the railway lines, because most of the railways are trying to use an optical fiber connection these days. Then this is the method we are using for a blown into conduit. Here a blower is used where a conduct from one side is actually entered another, and then from the other part an optical fiber is at the particular pressure is blown into a conduit. So it's very a simple process again for all the engineers present over there. You do not have to worry about the much strength over present or applying over there. Now, this is the method we are usually seeing in India. We are always having the aerial poles. We are usually seeing at the highways an orange color optical fiber always lying around through the trees or from the poles around the highways. Then these are some of the equipments using at the time of the optical fiber installation. This is a pulling tape. Actually, we have a support structure and we having all the tapes surrounded over there. So it's very important to take carefully to take out all the optical fiber pulling tape from this. Then we are using this structure you are looking at over here is this one. We are using this to attach an optical fiber through a cable, which actually makes a equal amount of pressure throughout the optical fiber. Because if we are applying a single force from the one end of the optical fiber, it's very difficult for us to hold it at the same pressure. So it's very important to use this kind of swirls over there. It will take a particular pressure at one moment and it will not break down all the optical fiber suddenly. Then this is the process I told you earlier, day before yesterday, that we do not have to put it in the vertical manner, the drums of an optical fiber. We always have to take the drum in the horizontal manner. So again, why I tell you the reason is because all the optical fiber will present like this over here. It will be curved like this. So the least most optical fiber will be suffering from more pressure from upper optical fiber. So it may break down all the optical fiber from there. So it's very important you should always take the care of an optical fiber in the horizontal direction like this. So there will be a equal pressure on optical fibers. So they will not break down from their own weight. Then if you are having a numerous number of drums over there, so how you have to store it is the image is like this. That you do not have to put in the vertical manners. You always have to put it in the horizontal manners over here. Then how to storage if you are taking out all the optical fiber drums over there. So it's a rotation how you have taken out. And this is the thing I was telling you, always have to take optical fiber from the upper side of the reel. You never have to take it from the bottom of the reel. Now, whenever you are using an optical fiber and you are taking out all the optical fiber reel, so there are much excess of optical fiber which is left aside the construction site. So it's not like the thing is not like this that you have to lay optical fiber around this around the city like openly. We have a storage diagram for that. We always have to store optical fiber in a figure of 8. So it's very important for us that there is no much pressure at a single point, and plus it's very easy to solve a figure 8 for an optical fiber. So I show you one image why we use an 8 figure over here. As you can see, this is a backfeed method, or you can say where installation is being placed. This is the whole ground, or you can say this is the whole place we have to lay the optical fiber from one end to another. You can see these pits over here. These are actually the manholes. These are the manholes we are using to place an extra optical fiber over there. So you can see over here how we are using the optical fibers. So from one end we are using an optical fiber to enter to the another part. They have passed through one manhole and they have entered to the another manhole. Where while entering and they are using empty the whole reel, they are using an 8 figure over here to extend the optical fiber furtherly. They use these equipments to place to the other side, means they will taking all these equipments to the other side, and they will solve out the figure 8 very easily and will be blown by any of the method we have already seen. So again, these manholes are very useful for us for at the times of installation also and after the installation also. So they have seen the similar thing they are showing over here. So this was how we are actually doing all the installation process right now. So I have some of the videos for you, which will be telling you how exactly we are installing all the optical fiber. So now we are looking at the optical fiber trenching. So how exactly a trenching process is carried out through a installation of an optical fiber. This is a kind of machine they are using to means bury all the optical fiber, and they're cutting the holes from the roads. So very slowly it works around the roads. You can just make holes around the roads or side the road also in the sandy soil. So this is how they are making the holes on the road. So they are now clearing all the sand from the holes, because it's important to be a very subtle surface over there. Now they're placing a form so that there is a shock, all the shock absorbent over there. Now here they are laying the optical fiber inside the trenching. Here they are filling up all the holes.
864676. 864676.
So this is how they are able to lead the optical fiber installed. So this is how we are doing the trenching, and now we'll see how an optical fiber is blown through a conduct. So this is the reel I showed you before in the image.
To begin the fiber optic cable installation process, first install the pull tape. Using a duct rodder or similar tool, rod the inner duct. Once rodded, attach pull tape to rodder. Pull the tape into the conduit. Once the pull tape is in place, set fiber optic quadrant lock or appropriate device for the specific pulling situation. Then attach the fiber optic cable to the pull tape using a pulling grip. Puller setup. Next, mount the conduct's fiber optic cable puller on an appropriately sized square mounting post. Caution. Lift the fiber optic cable puller only with the proper equipment or sufficient manpower. Improper lifting techniques may result in personal injury or property damage. Attach the quick connect couplings to the power supply. Note, the fiber optic cable puller's hydraulic system uses quick connect couplings. Keep all connections clean to avoid contamination and possible system failure. Connect the hydraulic supply hoses to the foot control valve assembly. Ensure the pressure hose from the power source goes to the inlet of the foot control valve. Connect the hoses from the foot control valve assembly to the puller. The supply hose assembly has 4 identical male couplings and can be attached between the puller and foot control valve assembly in any orientation. Warning: escaping fluids under pressure can penetrate the skin and cause serious personal injury. Position the foot control and attach the capstan. The foot control valve assembly controls the speed and direction of rotation of the capstan. The further the foot pedal is pushed down, the faster the puller turns. Position the foot control valve at least 3 to 4 feet from the capstan's feet-off side. Position the foot control in the best possible location for safety and proper operation. Attach the capstan to the puller's shaft by aligning the capstan slots with the shaft's pins. Push the capstan onto the shaft until it stops, then rotate clockwise until it stops. Pull outward to lock the capstan into position. Make sure the shaft locking pins are visible through the holes in the capstan hub. Move the puller into its final position. The pull line will wrap best on the capstan if the capstan is angled about 10 degrees away from the pull line. This will allow the line to walk down the side of the capstan and push the previous wraps to the side. Place 4 or more side-by-side wraps of the pull tape around the capstan in the direction of rotation. Do not wrap more than 1 layer of pull line on the capstan. Start the hydraulic power source. Pulling operations. Slowly press the foot control pedal to check pulling direction and ensure hydraulic hoses are connected properly.
Note, switching the quick connect couplings on one end of the hose assembly between the puller and the foot control valve assembly will reverse the direction of capstan rotation.
Resume pulling. Remove any slack or excess pull line before increasing the puller's speed. Attend the line coming off the capstan to avoid any tangles and keep some tension on the line so that the capstan grips the pull line. Never wrap the line around your hand, arm, foot, or leg, and always be prepared to release the line. Stand at least 3 to 4 feet away and at a 20-degree angle from the capstan. Wear gloves to avoid rope burns and abrasions.
Caution. Stand to the side of the pull line to prevent injury in case it breaks. Always wear protective equipment, hard hat, safety glasses, safety shoes, and work gloves. Warning. Stay clear of the rotating capstan. Severe personal injury or death could result from entanglement with it or the pull line. Follow these safety precautions. Do not wrap the pull line around a hand, arm, foot, or leg. Always be ready to release the pull line. Important. Proper cable pulling lubrication may be necessary to ensure safe and successful fiber optic cable installation. Contact Condux International for pulling lubricant specifications.
When the tension limit control is on, the puller will stop pulling if the cable tension exceeds the programmed limit of the electronic control box. Release the foot pedal, and the cable or pull line tension will slowly release. Slowly reverse the puller to release cable or pull line tension by lifting up on the foot pedal. Many pull lines build up tension from stretching. Never approach or service a pull line under tension. Always release tension before proceeding. When the electronically programmed tension overload limit is set higher than the adjustable relief valve, the puller will stop when the relief valve setting is reached. If the pulling operation exceeds the electronic tension limit or relief valve setting, correct the cause for high tension. Electronic control system. The electronic control box power switch should be in the off position before connecting or disconnecting any cords. Connect the sensing cord from the electronic control box to the load cell mounted on the puller. The 6-pin female connector on the end of the cord mates with the male receptacle located on the load cell. Tighten the connector collar over the threaded portion of the receptacle.
Note, before making any connections, ensure the receptacle is free of dirt and moisture.
Connect the valve control cord from the electronic control box to the foot control valve assembly. The 2-pin female connector on the end of the cord mates with the male receptacle located on the side of the foot control valve assembly. Tighten the connector collar over the threaded portion of the receptacle. The 2-pin connector on the front panel of the electronic control box supplies electrical power to the electronic control box. This power can come from a vehicle's power point or its lighter socket. The electronic control box requires 12-volt DC power for proper operation. Connect one of the power cords to the 2-pin connector on the front panel of the electronic control box. Connect the other end of the power cord to a 12-volt DC power source.
Danger. The main power switch supplies power to the indicator and chart recorder. When a power supply is connected to the electronic control box, portions of it are energized. Follow all electrical equipment precautions. Note, always disconnect the power cord when the electronic control box is not in use. When the power cord is connected to the electronic control box, it energizes portions of the control box. If the power cord is left attached when the control box is not in use, the control box will drain the power supply. Caution. Damage to cable may result from excessive pulling forces. Use precautions to safeguard against overload conditions.
Figure 8 cable. In bidirectional pulling applications, it may be necessary to figure eight the fiber optic cable. Figure eight cable in a clear area free from debris or obstructions. For more information on the Conduct's fiber optic cable puller, contact.
So this is how we do it through a blowing conduit. And then we have a installation process in the underwater, how exactly we are installing it underwater. So this is how we are laying the optical fiber undersea, and in the undersea we are not using the optical fiber in the same structure. So we are having a different kind of structure cabling in for the underwater sea. I'll show you some of them.
Hello, excuse me, sir.
Yes.
Sir, in this video, we are seeing that the sea level is like is smooth level and plane. The surface of under the bottom of sea is like is smooth surface, but actually it is not.
Yes, sir.
In
Actually,
practical.
that surface is very nearby to the shore. So beside the seashore, you have a very plain or a smooth surface. So at that time only we are using that kind of a rover. But in the
That
later
means
part,
we have to go parallel with the seashore or
in the starting you have to go through a seashore. Afterwards, only you are able to move into the deeper side of the sea. So at that time, you just have to lay down all the optical fiber on that type of terrain. You can see at the bottom of the sea.
Sir, for
So
what about for deeper sea, deep sea, for deep sea region?
we are actually having a tour. Firstly, we do not just go for a optical fiber laying over there. We first have a tour around all the thing. We go through a submarine over there. We have ultrasounds over there. So we see and look for the depths of the sea over there. If there it's too much underwater, we do not lay the optical fiber over there. We actually try to take a route which is very not deeper, or an optical fiber can hold that type of a pressure over there. So
So,
it's very
in general, how much depth we prefer to lay down the optical fiber cable in the sea?
still now we don't have any type of an means you can a maximum limit we can have in, because in Arabian Sea we have a very much depth over there of 400 meters till 400 meters.
General depth
So
of sea we prefer to lay down the cable. Maybe you can tell us.
I'm not getting your voice.
Sir, the general normal depth of sea which we prefer to lay down our cable in the sea.
We cannot say we have a preferred depth over here, because in every continent and country we having a different depths. Because if you see at the Indian's oceans, we having a starting depth of 40 meters, 30 meters, and afterwards we are going to the 100 to 200 meters. But in Australia side we having a depth of near about 200 meters. So again, it's not preferable for a particular countries. We are setting the standards according to the depth of the seas over there. So we having a different kinds of optical fiber laid throughout the countries. Only in the particular part where we are actually having all the ultrasounds over there, and we know all the depths over there. So the maximum we can go is about 200 to 400 meters. Not for much more than length, we are producing a more high tensile optical fiber with the high surroundings, or you can say higher steel rods with it. So I'll show you. I'm trying to show you a image over here, which actually representing an underwater cable. So according to the depth, we can manufacture that kind of cables over there.
Sir, one question is there. One more question is there.
Yes.
Is there any kind of other type of protection we are providing to the optical fiber cable under the sea?
Yes, we do have another kind of protections over there also. We generally do not use any single type of optical fiber over there, similar structure we are always producing. We have a different cores and different diameters plus different materials also on the optical fiber to secure it from the pressure of the underwater or from any other reasons also. So I'll show you one of the cable over here. So this is a kind of a structure we are having for the underwater cable. So you can look over here, different kinds of materials and polymers and much more armors we are using over here to protect an optical fiber. So we are having a single optical fibers coming out of this copper conductors over here, and rest all of this is a armor for an optical fiber which is being laid under a water. So we are adding a much more protection for an optical fiber. And we have a similar structure over here also.
Sir, one more question is there, sir.
Yes, please.
Sir, can we lay down the cable floating in the water, so under the depth of 20 or 30 meters from the surface of the water?
Floating beneath this much height will be a bit difficult, because there are very large ships moving around in the you can say all around the region over there, and plus submarines, military submarines are over there. So every time we try to lay a cable, we do not hang it into a mid of any particular sea, because it's very dangerous for us also, and plus the species present over there. So we always try to put it on the depth of the seabed over there, because again it's very not reachable for every person over there. Plus, we are trying to maintain optical fiber over there so that we do not have to repair. Don't have to go for repairment again and again. So we are placing that optical fiber from you can say from this year, and we will be using that same optical fiber till 20 to 30 years from now. And I tell you a fact that the cables which were laid from 1980s, near 1980s in the sea, from USA to France. So we are still using that optical fibers right now. They are still in the use right now. So we try to go for the depth only. We are not providing it at a particular float in the optical in the sea level.
Yeah, fine, sir. Fine. Thank you, sir.
Okay. I tell you one thing that a few years back in India there was a connection cut in the internet and all the Google sites were closed from that day. Some of them gave a reason that some of any of the military army ship actually drop an anchor over the optical fiber. So it was a theory that they start thinking that this was the fault of a military, but few videos actually reveal that there is only not the anchor or the human mistake for the optical fiber destructions. There are actually animal species, you can say the fishes, who is actually trying to eat the optical fiber underwater because they do not know exactly what is that thing. So for them, there it's a harmless for that, so they try to demolish all that thing. So I have a video for that showing a shark is eating an optical fiber. So it was recorded by a man who went for the repairing. So here we can see from a drone. We have over the left hand side we have a shark and an optical fiber laid over there. And they didn't know it's harmful for the species living inside the sea also, plus for the optical fiber also. So we do not have we have much of an you can say repayments going on in the under the water again and again because of this type of incidents happening in the sea. So this was one recorded for officially, which was launched by to show all the companies they're actually having this kind of problems in the seabed. So they try to bite or they cut the ropes from inside. So sometimes we having a disconnections from internet and more service from other countries also. Plus, I want to tell you these optical fiber are not only used for internet purposes or something else. We are also using for the calling also. All the international calls we are doing from India to USA or to Africa or to even to Australia also are going through an optical fiber link. So I have a map over here which actually shows all the optical fiber links throughout the world over here. So this is the map we can look over, which the whole optical fiber is being laid underwater from country to countries. So we have different kinds of optical fibers laid out from 1980s till 2016, and we are still going on for the optical fiber links because they are very useful and very fast to operate. Plus, there is no damage, and plus very nearly less losses comparatively to wireless communication or to satellite or to a normal cable connections over there. So this is how we are planning, and we are trying to develop an optical fiber throughout. So some of the companies are actually not only working on making a glass of an optical fiber. Some of the companies like Corning Glass we have already seen who are making the optical fiber for the countries. Plus they are making the optical fiber the glasses for our cell phones, smartphones also. So they have developed a future thing that they have a perspective. While using a optical fiber glass only, they are able to take on all the technologies, the new technologies they are going to have. So they made a video for that, which is called as 2050 Future Technology. So I have a day in future video for this one. So this is how they are using an optical fiber glass for different technologies also these days. So this is how they are taking the optical fiber glass to a new extent now. So they have developed numerous of number of things from an optical fiber glass only, and plus the optical fiber techniques they are using, because it's lightning fast and they can operate multiple things from an optical fiber. So this is how they are using the bandwidth of an optical fiber to operate or to make the new technologies in our future coming. So this is how this is all the thing we were have to see in the installation part and plus the future part of the perspective of an optical fiber. So I show you some of the things. These are the particular number of another machines which are used for in trenching also. So this is used for the heavy heavy areas only. Like if you are going for a mountainous region, so we are using that kind of a machine over there. And for the manual digging or manual trenching, we are using the manpower over there to develop a huge trench over that place. It's even for that place which are where the soil is very soft in, or you can say we cannot rush a machine heavy machinery over there. So at that time we require a man force over there. So this is how engineers go underwater to repair the optical fiber, because at the seashores it's very important to cover up the optical fiber through very heavy armor from there that way. Like a conduit we are using it for the underground, we are using a very heavy rod metals, or you could say metals like structures over there, so that if there any ship also or drop their anchors at that place, it should not avoid any communication distraction between the optical fibers between two countries. So they have to keep on repairing in the seaside shores also over there. And if we are planning for a optical fiber link, like I talk about, they have to go for a link route. So how they are going over there is that they have to firstly plan an optical fiber route. Means if we are planning an optical, we take an example over that. If I am planning from my office to NITTTR, we have a route, multiple routes over there. So we are planning to dig an optical fiber from our office to an NITTTR over here. So we firstly go for the permissions. If we got the permissions, we look for the our best effective route for there. We have to follow that best effective route with the contractor. So whichever we will be finding the best one, where there will be less turns or will be consuming less optical fiber, we'll be finalizing that route, and then only we'll be start working on that. And according to that area, we'll be using our equipments list over there, plus the how much manpower will be required, we'll be deciding on that basis. Plus we will be going through trenching or underground or from the aerial routes. It will be decided according to the areas present over there. As if we have Chandigarh, we have numerous amounts of trees and poles over here, so it will be very easy for us an economic way that we go for a aerial route from there, from tree to tree, or at some good parts of the city we can lay the optical fiber from the underground part. So this is how we install all the optical fiber throughout, and we have to follow this procedure in step-by-step portion only. If we go across, we start digging around the city like with no permissions or with no paperwork done, they may be not allowing us to dig the or install the optical fiber through the city. So it's very important to take the step very seriously and install all the optical fiber. So this was all about the installation of optical fiber, and we have already done through the splicing part also. And I like to show you one device also which we engineers actually use at the time of a survey for link route, and the device is called as the GPS, and it's a GPS. You can see many of you must have seen this GPS in the RF trackers also. So this is the kind of GPS they use for tracking all the positions or the particular point they have to reach. They just put the latitude or longitude inside the GPS.
Yes, at Government Engineering, Bharatpur. Yes, sir. Government Engineering College, Bharatpur.
Hello. Hello.
Yes,
Yes,
sir.
sir.
Yes, sir.
So do you have any question regarding the same?
No, sir.
Okay, okay. Thank you, sir.
Thank you, sir.
Yes, at
No question, sir.
sir, how did you find this lecture?
Hello.
Hello.
No question, sir. कुछ पूछना है?
Good afternoon, sir. Okay, आपको sir everything is clear for you, sir? कोई भी अगर क्वेश्चन या क्वायरी हो आपकी? Sir, do you have any query regarding the...
At Shri Balaji.
No, sir. No.
Okay, okay. Thank you so much, sir.
Okay. Thank you, sir.
Okay. Anyone from here have any questions? Everything's clear for you for the installation part of an optical fiber? Okay, then I will be closing this session for this one now. So this is how we exactly go for an optical fiber installation process throughout the industrial part of the view. And we have numerous steps to follow to do the installation, and we have to take particular permissions from particular departments also while do the installations. So this is how all the videos I have to show to you for installation, because we cannot show the equipments because it's very heavy and to be used outside the premises only. So if you have any querying or any demonstration to be done again, you can ask for that. We'll be present here for you again. So this will be done for your this session, and we'll carry forward then after your lunch break.
Yes, this lecture is available at our right now. This lecture is available at our YouTube channel NITTTRCHD Chandigarh 1. And after that, we will edit this lecture and it will be available at our web portal NCTL. सर वो वैसे फर्स्ट डे ही मैंने शो कर दिया था.
Excuse me, sir.
Yes, sir. Please.
Sir, we are from Government Engineering College, Bharatpur.
Yes, sir.
Can we have the slides or presentations, PPTs on in soft copy in the pen or in mail or in anything?
All these people will be sent to you by course coordinator Dr. SPL Satyan at the end of this course.
Thank you, sir.
Knowing where these contents will be available? Have you ever visited our NCTL portal? कितने बच्चों ने आपको है? इस इलेक्ट्रॉनिक्स के देखिए और कुछ सब्जेक्ट से देखिए. इसके देखिए. इस टीचर के देखिए. जोर से बोलो इतनी घबराहट करो.
All are subject teachers.
All subject teachers. Just name 1, 2.
Kanika ma'am, Mehra sir, and Suchal.
तीनों के आपने जो लेक्चर देखे हैं उसके ऊपर क्या पूरा सब्जेक्ट कवर करते हैं आपका कोई कंप्लीट सब्जेक्ट?
Yeah, I have seen only 2 or 3 videos.
2 or 3 only. आपने आगे की लाइन से आप लोगों ने नेवर सीन? ओके. आइडिया नहीं था या टाइम नहीं मिला देखने के लिए? आइडिया. तो ये पूरा इनको बताओ.
Yes.
कि where these videos are available.
Yes.
बताओ. बताओ and give that link also to all of them.
All right. If we talk about this lecture, then we just have to go to YouTube. Yes, sir. Then you have to type NITTTRCHD at the search option. then you can find this four channels of our institute. You can see live now at the end of the bottom of this channel. You have to just click this channel and you can there will be first video, live video you can see. So live video you can see. Take out all the optical fiber from reel. I'll show you a diagram over here that how you have to take out. अभी ये full day का lecture है, then after that हम इसको edit करेंगे, then it will be available on our web portal NCTEL. And we put a reel over here. Yes. For the optical fiber. So this is how we place optical fiber at the construction site. Then again, it's not like that you just start pulling down all the optical fiber. There is a process that you have to always. There you can see the different departments of our institute. You cannot just take it out from the bottom of the reel, because how much pressure you will be allowing at the reel, it will be taking out more and more optical fiber at a single time. So it's very important you always take out the end from the top of the reel. So it's very easy how much pressure you will be applying, only that much of the optical fiber will be coming out of the reel. So again, it's very important to look out for all the procedures and the steps to be carried out at the installation process. Then we are having the installation requirements, then the support structures as I already
These videos are available
shown you over here. You just have to click this video, then it will redirect to YouTube and you can watch this.
Even you can download on your smartphone also.
Yes, we have.
Downloading, how you will be downloading? FPQRV, Institute FPQRV. Just you need to go in.
Sir, अभी Android based है ना ये just. हाँ जी. Just you have to go to Play Store and type NITTTRCHD.
एक एक करके follow how the quality of audio and video and how the quality of PPT they are receiving one by one. कितने centers connected हैं आपके? 6. इनसे पूछो कि कैसी थी quality आपकी audio video की?
मोना ऑन करो. Hello at Government Engineering College Bharatpur.
Yes, sir.
हाँ जी, good afternoon, sir.
Good afternoon, sir.
हाँ जी सर, ये ड्यूरिंग द कोर्स आपको ऑडियो एंड वीडियो की क्वालिटी कैसे प्रॉपरली रिसीव हो रही है?
हाँ सर, प्रॉपरली रिसीव हो रही है, बस आज ही थोड़ा सा डिले आ रहा है, इससे पहले कोई डिले भी नहीं आया था.
ओके सर, लास्ट 3 days में प्रॉपरली थी आपको?
प्रॉपर चल रहा है, अभी प्रॉपर चल रहा है, पर अभी आज इको आ रहा है सर. इको मतलब किसी दूसरे सेंटर की आवाज हमारे को आ जाती है. मतलब जो आपने अभी लेक्चर दिया है वो विदिन 2 सेकंड, आफ्टर 2 सेकंड वी आर रिसीविंग द सेम साउंड अगेन.
सर वो किसी आई थिंक किसी सेंटर ने माइक ऑन कर लिया था ड्यूरिंग द इंटरेक्शन.
इको आ रहा था.
बाकी सर आपको पीपीटीज भी क्लियरली रीडेबल है जो भी अभी हम जितने भी एक्सपर्ट्स ने प्रेजेंट किए?
हाँ सर, ऑल पीपीटी और प्रेजेंटेशंस आर वेरी क्लियर एंड फाइन.
ओके सर, थैंक यू सर.
बालाजी से पूछो
सर वो डिस्कनेक्ट हो गया. एट नदरन इंडिया इंजीनियरिंग कॉलेज. Yes, at Nadran India Engineering College. Hello. Nadran India Engineering College. हाँ जी मैम. हाँ जी मैम, आपको ऑडियो वीडियो की क्वालिटी रिसीव हो रही है?
नहीं, we are receiving properly, no problem.
और मैम पीपीटीज वगैरह भी आपको क्लियरली विजिबल है?
Sorry, what you saying?
मैम पीपीटीज भी आपको क्लियरली विजिबल है?
Yeah, everything is just visible.
ओके, थैंक यू मैम.
एंटर करके ही मिलते थे हमारे सी बैठ के ऐसे लगते थे।
हाँ एंटर करके एक्स्ट्रा
आपको ट्रेनिंग से कितना टाइम हो गया यहाँ पे?
मैम टोटल एक्सपीरियंस इस कॉलेज का 10 साल।
इसी का भी 10 है और वैसे अदरवाइज
पहले 4 साल यहाँ पे था, पहले नहीं पढ़ाया तो 2 साल तक किसी भी में छोड़ के चला गया, 2 साल किसी दूसरे कॉलेज में वापस आया
वो डेलीगेशन से
गुड़गांव फरीदाबाद। टोटल एक्सपीरियंस कॉलेज वाले को 15-16 साल का
लगता नहीं पड़ा। टेक्नीशियन अपने सारे काफी वो है मतलब एक्सपीरियंस है ना। अंजलि का कितना होगा?
अंजलि तो
अंजलि का भी
बच्चे
बाकी चेतन सर, अमित सर का
वो भी अभी नहीं, उन्हें भी साल 2 साल के।
अच्छा अभी साल 2 साल इनके शायद उनके क्लास की तरह
नहीं वो
पता ना लगता वो
22-23 साल के 23-24 साल के बच्चे। हम सब तो पके हुए हैं।
आपका घर कहाँ पे?
नजदीक है 5 किलोमीटर शादी में।
कैसे जाते हैं?
बाइक से।
फिर जैसे पहले पढ़ाई नहीं चल रही फिर उसके बाद आपको कैसे सुनने का वापस आने?
मैंने एक दिन पूजा मैडम को ऐसे बोल दिया फोन पे, मैडम वापस आ जाऊंगा। ठीक है सर आ जाओ, रिज्यूम भेज दो। मैं ऐसे मजे में रिज्यूम भेज दिया, मैडम ने डिलीवर कर दिया। तुम यहाँ पे आया तो मैंने सैलरी बता दी, एग्री हो गया।
पर सीन तो फिर भी वही रहा 2 साल बाद ही बना दे।
नहीं मैडम अब ना दूर होने लगा था पूरा, 45 किलोमीटर एक तरफ से पड़ता था, तो मिल सर्वाइकल है, आना जाना बहुत समस्या होती है, इसीलिए मैं वापस यहाँ आया।
लोग टाइम की कदर नहीं करते, टाइम की जितनी वैल्यू उतना पैसे की वैल्यू नहीं है।
अब घर के नजदीक है, टेंशन होती नहीं है। कोई इमरजेंसी हो जाए, फोन आ जाए, मैं 5-10 मिनट में घर चला जाऊंगा। अब गुड़गांव में वहां पे कुछ दिक्कत हो जाए, घर में आऊंगा रहने तो सबसे दिक्कत।
अच्छा फिर हम ये तो फिर भी आप एक कंसीडरेशन ले रहे हो, दूसरी है थकावट। बंदा घर आके उस एनर्जी से थोड़ी घर वालों से बात कर पाता है जैसे आप कर पाते हो गया, तो वो बहुत बड़ा मैटर होता है।
तो मेरी मैडम मेडिकल दुनिया भर की पड़ी हुई है, छुट्टी नहीं ले पाते, मन ही नहीं होता। अब भागने की क्या है ना, या तो पूरे दिन की छुट्टी मारनी है। अब उन्होंने रूल बना दे मैंने तुम्हें 2 ही लेनी है, तो वही 2 बड़ी मुश्किल हो जाती है, तो छुट्टी नहीं ले मन होता है। घर के नजदीक काम करने के फायदे बहुत हैं।
मेरी मदर को बस यही यहाँ का एक और डिसएडवांटेज है कि दूर जाते हैं।
आप कहाँ से आ रहे हो? आप दूर और वो है सो तो मेट्रो चल गई, मेट्रो की वजह से फिर भी
सब लोग जॉब सभी चली मेट्रो की वजह से नहीं है, नहीं तो कहाँ पॉसिबल है। पहले मैं 1 साल में बीटीसी करी है ग्रेटर नोएडा, तो वो तो इससे डबल पड़ता था मेरे।
हाँ बीटीसी जितना वहां से यहाँ हो उससे ज्यादा आगे फिर आगे जाना।
वो 75 किलोमीटर था, ये 40-45 पड़ता है।
बीटीसी में कौन है जो कौन थे आप?
बीटीसी तब तो नीलम नाथ थे ना डायरेक्टर, वो ईसी के थे, तो बस वही देखी। तब तो मैं तो चले गए, अभी प्रेजेंटली पता नहीं मैं मेरी
प्रेजेंटली तो डॉक्टर जितेंद्र पाठक,
वो उन्होंने उसी समय ज्वाइन किया था, तो बस मैंने तब छोड़ दिया था कि मेरे भी बैकएक रहने लग गया था।
हाँ लंबा डिस्टेंस में ट्रेवल करोगे ना तो बहुत दिक्कत होगी।
फिर शरीर ना खराब करना आसान है, संभालना मुश्किल है। मतलब हस्बैंड कहने लगे कि छोड़ दो, मैंने इमीडिएट रिजाइन दिया। मतलब डॉक्टर कहती कि इस तरह से बढ़ जाएगी धीरे। तो कौन कहती पिलो लेके जाओ मेट्रो में बैठने के लिए, इतना
अच्छा नहीं लगता ना पिलो लेके जाओ।
और बैग में और क्या क्या खाना पानी ये वो। अब कल जतिन से कहने लगे कि यहाँ का पानी मत पिया करो, मैं तो ये पानी पूरी उठा के नहीं ला सकते हम।
मैंने इतना नहीं करना चाहिए कि पानी और ये सब सोच के
रहना तो यही है ना, हवा तो यही है।
हेलो 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 हेलो
ये जो हॉस्पिटल है यहाँ बगल में, क्या नाम है इसका?
जग प्रवेश।
जग प्रवेश, ये गवर्नमेंट है? भीड़ बहुत होती है ना।
हेलो, हाँ जी, नमस्कार जी। हाँ हाँ सर, नमस्कार। वो एक्चुअली ना अब ये नंबर ना मेरा फोन नीलम के पास है, नीलम का फोन मेरे पास है ना, तो मेरा जो नंबर है आपके पास में, बात करने को मैं दे देता हूँ। हाँ मैं अपना दे देता हूँ आपको, हाँ नंबर दे दो। हेलो, हाँ लिख लीजिए, 9971912450। हाँ जी, इस नंबर पर। आज ना फोन ना वाइफ कहने लगी अपना फोन दे के जाओ, इसमें ना वो रिलायंस जियो वाली सिम लेके आएंगे, तो वो तभी देते हैं जब फोन होगा आपके पास में। ठीक है भाई, फिर मैं कैसे करूँ, क्या मेरे ले आओ।
तो आपने बुक करा ली थी?
बुक क्या है, वो बारकोड वगैरह जनरेट करना है, वो मैंने जनरेट कर दिया था। फिर रिलायंस का जो हमारे यहाँ पे है, वो उसकी यहाँ पे जाओ तो वो दिखाना पड़ता है और फोन दिखाना पड़ता है कि जिससे वो जनरेट हुआ है। तो वाइफ लेके गई थी, वहां पे गई तो वहां पे भीड़ भी थी, तो कहने लगी कि उन्होंने तो ऐसे कूपन लाया कि बाहर लाके ऐसे फेंक दिए, जिसके जवाब लगे ले आओ। तो क्या मेरे तो नंबर ही नहीं आया, मैं फिर वो तो आना नहीं था, मैं घर आ जाओ ब्लैक से ले लेंगे, वो ठीक है।
तो फिर अब हो जाएगा?
नहीं, ब्लैक से होगा, आज से 200-300 रुपए में गारंटी मिल रहा है, वो ले लेंगे।
हम लोग गए रिलायंस डिजिटल, तो कहता रजिस्टर है, एंट्री कर दो फिर कूपन मिलेगा। अच्छा मिला, ठीक है कर देते। गए रजिस्टर देखा 21 सितंबर की एंट्री करनी है आज।
अच्छा,
इस संडे को गए थे हम कि आपको 21 सितंबर को आना है, तब सुबह आते ही कूपन ले लेना है और तब यहाँ पे काम होगा। अभी तो इतना टाइम नहीं है हमारे पास, हमारा भी चल रहा है।
वाइफ के पास भी फोन है, उसमें भी नेट है, ये इसमें 2G है पर अनलिमिटेड है। मेरे पास भी 2G है, अनलिमिटेड है, काम हो जाता है, ऐसा कुछ हुआ है नहीं। क्या करना था, व्हाट्सएप होता है, फेसबुक होता है, ईमेल होती है, ये सब इस पर काम हो जाता है। आपके हस्बैंड क्या करते हैं? एरिक्सन चाहिए।
हाँ पहले हम दोनों यहाँ से, मैं ग्रेटर नोएडा जाती थी, ये नोएडा जाती थी।
अच्छा, तो
साथ का कोई सीन नहीं था, ये कैब से जाते थे और मैं मेट्रो से जाती थी। तो फिर इन्होंने वापसी आना 10 बजे, 9-10 बजे, मतलब ट्रैफिक इतना ज्यादा होता था रास्ते में। अब अच्छा बॉस का बड़ा फर्क होता है, जैसे अब से मैं यहाँ पे भी वही चीज है, बॉस बैठा तो आपको बैठनी है, तो आप नहीं बैठ के ऐसे तो नहीं 9 से 5 की है, फिर तो मैंने 5 किया। तो जब अगला कह रहा है कि भाई काम है, वो बैठा हुआ काम कर रहा है, चाहे आपको बैठ के ये बच्चों को मैं यही समझाती हूँ, जब तुम आज लगता है ना कि क्लास क्यों लगानी है, ये है वो है,
खाली क्यों बैठे रहते हैं, एक एक्सपेरिमेंट के बाद क्यों नहीं करा रहे,
कुछ नहीं हनेल तक नहीं भागा अपनी कुर्सी से कि शर्म के मारे कि अब मैं कैसे जब बहुत बैठे,
कुछ भी नहीं सकते कि जाए क्या।
मेरा ब्रदर अभी उसका भी ज्वाइन करा, उसने 1 साल हुआ अभी यहीं शुरू करे दिल्ली में। उसकी हालत ये होती है कि जिस दिन बॉस नहीं है, हफ्ता या दूसरे ऑफिस के, तो उनकी है 9 से 5 मतलब 9 से 5, जैसे ही जिस दिन वो आ गया तो बैठ रहे हो 10 बजे तक।
अच्छा, बॉस भी बड़े कमीने होते हैं, मैंने से उन्हें भी ना काम है, काम भी पता कब याद आता है, जब छुट्टी का टाइम होने वाला हो ना, उस समय वो ऐसा काम लेके बैठ
अच्छा
जाते हैं।
कुछ तो बनना तो 9 से 5 के हिसाब से मोटे पॉइंट्स ले आ रहे 8 बजे पहुंच जाते थे मतलब हस्बैंड, और बॉस तो आ रहे 11 बजे, वो आई इस माइंडसेट से रहे ना कि हमें 8-9 बजे घर जाना है, उससे पहले जाना ही नहीं, निकलना ही नहीं है।
ये चीजें याद है,
बहुत फर्क पड़ता है। तो अब जी इनके बॉस है ना, अब वाले ऐसे हैं, वो खुद 9 से 5 मतलब 9 से 5 इनके ये होता है ना, यूजुअली गधे की तरह बैठे रहो, जो काम पूरे दिन में हो जाए मतलब ऐसे बैठ के हो जाता है, वो 9 से 5 में भी हो सकता है, करने की नीयत होनी चाहिए। तो अब वो भी ऐसे हैं कि घर जाके बच्चों को पढ़ाते हैं और प्रॉपर्ली, तो इनकी टाइमिंग भी बदली है 9 से 5, मतलब अगर वो बंदा बैठा है वो खुद कह देता है कि आप जाओ, कोई जरूरत नहीं है मैं अगर कोई काम है नहीं सही
काम का ना एक माहौल होता है, एक टेरर भी होना चाहिए। जब आपके दिमाग में रहेगा ना ऑब्जर्व कर रहा है, आप काम कर रहे हो तो आपको कोई ऑब्जर्व कर रहा है, आप काम नहीं कर पाओगे, फ्री हैंड
आप रिस्पांसिबिलिटी दो, छोड़ दो और उस पर्सन को नोटिस करो कि वो कैसे रिस्पांसिबिलिटी बिहेव कर रहा है, नहीं कर रहा है, उसके बाद थोड़े लगाए जाते हैं, यूं नहीं कि पहले शुरू करो करो करो।
हम आईटीएम में थे मैडम, सैलरी मेरे ख्याल से इससे अच्छी कोई कॉलेज दे ही नहीं रहा होगा एनसीआर में, जितनी अच्छी उस कॉलेज सैलरी दे रहे, टेक्नीशियन तक भी 50,000 में। तो वहाँ पे दिक्कत सिर्फ क्या थी, फाउंडेशन ये है, मतलब बंधन सा है, वो बर्दाश्त नहीं होता। जब तक फ्री नहीं छोड़ोगे ना काम करके, मुझे काम दे दो, आप मेरे सेटअप करना, वो मेरी जिम्मेदारी, कैसे करूँगा मैं कर दूंगा, और आप मेरे सर पे खड़े रहोगे, आपने क्यों नहीं किया, 10 मिनट तो हो गया आपको इसी में लगे, वो काम नहीं हो पाता। इस कॉलेज में ये चीज नहीं है, यहाँ पे ये है कि अपना दे दिया कर दो। अब थोड़ा सा डायरेक्टर सर आके गाँव ले लेते बच्चे, वो तो देखो मैनेजमेंट वो नहीं होना,
आपको लगता है कुछ हो पाए
बच्चे नहीं है, ठीक है हम भी मानते हैं गलत है, बच्चे नहीं है, तो उसके लिए पॉलिसीज कौन बनाएगा, मैं तो नहीं बनाऊंगा, आप तो अपर लेवल पर बनिए, आप सीधा डिसाइड कर दो, स्ट्रिक्ट एक्शन लेना पड़ेगा आपको, नहीं आएंगे एब्सेंट है तो डिटेन है।
F13 सेक्शन की पूरे दिन में कोई क्लास नहीं होती है, सिर्फ मेरी क्लास होती है, वो भी लास्ट लेक्चर। क्यों होती है? क्योंकि मैं अटेंडेंस नहीं दे रही, कि प्रेजेंट हो तो हो, नहीं तो नहीं।
उसके बाद
पूरा दिन चाहे कहीं भी घूम लेगा वो बच्चा, पर उस समय वो वहाँ पे बैठा होगा और टाइम पे बैठा होगा, क्योंकि मैडम लेट आने में भी अटेंडेंस नहीं देगी।
इसमें एक चीज और ऐड हो गया ना, तो जो रेगुलर आया बच्चा उसके मार्क्स अलग हो गए, तो जो परसेंट हो रहा है नहीं आ रहा है, बंक लगा,
जब तक ये नंबर बांटने नहीं छोड़ेंगे
तब तक कुछ नहीं। आईटीएम में ऐसा नहीं था, वहाँ पे क्या था, आप डिटेन है तो उसमें मतलब डिटेन है,
चाहे पैसा लगा लो चाहे जैकेट लगा लो।
और लैब में क्या था, आप चिट्ठी करते हुए किसी को दे देंगे ना स्लिप में,
हो गया सर अभी करके आया लो अपना करना है सर, तो सबके पास तो कूपन है, अभी सर ताला लगाओ, सर ने कूपन बांटे थे, 1 बजे कूपन बांटे थे,
मैं तो क्लास 3 चलाया, मैं कह रहा था
1 बजे तो क्लास स्टार्ट हुई होगी शायद, 2 छुट्टी होगी। सर आपने सर को बोल कूपन कैसे दे दिया? सर खाना उठा कर दिया उसने, 1 बजे कूपन बटे, 1:15 पर हम लोग वहाँ पर थे, 1:15 से और उसने 2 बजे तक खाना खाया है, तो बच्चे स्टूडेंट तो खाते हैं 12:30 से, क्या खाना खाना आपको ठीक है, मेरे पास कोई इसके लिए तो वैसे आप मेस वाले से डायरेक्ट खाना तक लाता है, एक्स्ट्रा लोगों को टिफिन भी देता है, और यहाँ से कुछ लोग वो वही बोल रहा था कि कुछ लोग बिना कूपन भी पहुँचेंगे, उनके कूपन बाद में लेगा, पता नहीं कैसे वो कंसिडर करे, खाना हो सकता है इसलिए चले जाए, अभी आप चले जाए बस आपको मिल जाएगा, क्योंकि खाना खा रहा था सारे तो बैठते थे सब। नहीं मैम अभी आएगी 11:15 बजे आती है एक बार। उसके बाद इवनिंग का सेशन खत्म हो जाएगा 4 बजे। कल लास्ट है। तो 4 डेली 4 तक का है। टाइम टेबल तो आपने देखा होगा सर। ये अलमारी के ऊपर लगा दे इसके लिए। ऑडिट वाले मैं तो पहचानता भी नहीं ऑडिट वाले यहाँ अपने बड़े सर है नहीं बड़े सर अच्छा पहले तो सर मैडम मैथ्स में नहीं करोगे अब तो ऑडिट में क्या है ऑडिट तो वैसे ही होगा जैसे होता है क्या कर लेगा यहाँ तो क्या क्या खा लेगा कद्दू को छोटी सी कद्दू का क्या है ऑडिट में मैंने सब कुछ ऑडिट वही होता है तो किस चीज की बात है किस चीज हाँ कद्दू थोड़ा कम चावल तो मैडम कंपल्सरी होता है किसी भी जमाने में तो खासकर दाल चावल और सब्जी ये तो मैडम डेली होता है दाल चावल और सब्जी चावल तो डेली दोपहर में पड़ेगा रात को नींद आ जाए तो रात को जो है जम जाता है तैयार करता दोपहर को सही
ओल्ड टाइम चावल ही चलता है
उधर क्या चावल
इलाहाबाद से इलाहाबाद की जो बेल्ट है वहां से जितना आगे जाओगे बिहार की साइड वो मतलब हमारे पूर्वांचल स्टार्ट हो जाता है वहां पर चावल नहीं होता है
मैं नहीं उसको 2-4 लोग और तो तुम्हारे पास में दो
नहीं इन लोगों ने बोला था पहले ही दिन
पहले दिन जो खाना बनाता था चावल सुबह नींद से चावल नहीं है तो लोगों का चावल तो सब जगह मिलते हैं दाल और चावल तो
अरे वो पॉट ले गए वो पॉट भी आ रही है जूम ले गया
काम करने का चार्ज रिलैक्स हो रहा तो होते मैं तो इसीलिए आज चार्ज भी खाना
बस कल परसों ही तो है रात में तो खाते हैं अब लास्ट में आने की
आले पता नहीं
हां से हम तो समझ रहे हो
शाम को ऐसे तो शाम को खाना करते हैं बनाते हैं चलो खुशी की तो बना दो सुबह से एनर्जी होती है एनर्जेटिक रहते हैं सुबह जो बोलो बना एक बार टाइम कैसे पढ़ के टाइम कम पड़ता है शाम को सही में कर जाते हैं शाम को ऐसे ही मुश्किल से लगाते हैं सही है
पता नहीं क्या था लोग इन्हें तो पता नहीं क्या था मतलब किसी का तो हो गया गंजा
अरे नहीं आता तो है बनाती
ये सभी कहते हैं आप तो मुझे भी बताता नहीं
रोटी पड़ी जो नहीं बनाती
अभी तो मैं कह रहा हो गया किसी का तो गंजा आप यानी वो बर्गर के लिए जो मैं ये चिंता रहेगा
बोलने की बात बड़े उससे कितना रहोगे
ये आज के टाइम में
रहने दो तुम रहने दो हमको मैं खाने के लिए तुमसे पूछेंगे
मैडम वो कह रही थी
हम भी आजकल की रामवा से बहुत
आज की बुरा नहीं मतलब
हमारी ना आपको थोड़ा टाइम बना के देगी सेवा करेगी बस खाली
करने वाले मैडम सब करते मैडम को एक्सरसाइज नहीं करती जो करने वाले जो करेंगे
तो भाई एक और काम
जिन्हें नहीं करना हां जिसे नहीं करना उसकी जॉब नहीं करेगा
अरे सुनो भाई वैसे तो ये बोलना ठीक है क्योंकि मजबूरी है अगर आप अपनी वाइफ से जॉब करवाओगे तो आप क्यों करवाते करते ही बताओ
क्यों करवा
ऐसे ही नहीं कमाओ
एजुकेशन के लिए बेकार है
अच्छा एजुकेशन करने का मतलब जॉब करने का कमाओ हम सब कमाने के लिए कमाई करने के लिए क्या
आपने
कमाई करने के लिए पढ़ाई की लड़की ने एजुकेशन के लिए कुछ नहीं है आपने ठीक है
5-6 साल मेहनत करे
देखो ना तुम लड़की से कमाई करवानी है लड़की से कमाई करवानी है अपनी वाइफ से
अरे कमाई नहीं है
तो फिर क्या
आप कह रहे कमाई कराने के लिए हमारे जरूरी नहीं हो
जॉब पर क्यों मिलोगे
आप भी का टाइमिंग वैसे क्यों
उसकी अपनी मर्जी हो जॉब पे जाओ
तो आप जो कह रहे हैं ना कि पैसे कमाना ये मोटिव क्यों
साइकिल में करा लो
क्या
बीमा करा लो अपनी मर्जी से
फ्री में तो सर कोई नहीं करेगा
कैसे तुम कैसे कह रहे हो समाज सेवा करवाओ ना उसके मन में हो पेड़ लगाने का पेड़ लगाओ उससे समाज सेवा करवाओ गरीबों को
ये हमारे टिकट बात है
वही तो मैं कह रहा हूँ लड़की से कमाई कराने का शौक है लेकिन तुम घर में
ये कमाई करने की बात होती है लड़की एजुकेशन नहीं हुई है
मतलब आप अपनी वाइफ से जॉब करवा सकते हो लेकिन उसकी हेल्प नहीं कर सकते आप दूसरे में हेल्प कर नहीं सकते
मैं वो नहीं कह रहा जो सर कह रहे हैं ना कि कमाई कराने के लिए लड़की ने पढ़ाई कर एजुकेशन
अच्छा अच्छा एक मिनट अरे अभिषेक ये वो बताओ कोई आदमी एक मिनट ये बताओ अरे अभिषेक एक मिनट बताओ मैं सुन लूंगा अगर हमने शेफ को कोर्स कर लिया तो तुम खाना बनाना सीख लोगे नहीं सीखोगे तो तुम्हें शौक है अगर तुम घर में खाना बनाते हो वो तुम्हें हेल्प करो अपनी पत्नी तो हेल्प करने में क्या बुराई है जब वो तुम्हारे लिए बाजार में जाके मतलब वो जाके जॉब कर सकती है तुम घर में उसकी हेल्प नहीं कर सकते भाई आज वाइफ जॉब नहीं मेरा सजेशन चाहते हो कि आपकी वाइफ जॉब करे, आप घर में हेल्प करो उसकी, खाना बनाने में हेल्प करो, सफाई करने में हेल्प करो, बच्चे पालने में। ऐसा है ना, ये चीज ऑप्शनल है। अगर जैसे आप अपनी मर्जी से जॉब कर रहे हैं वो अलग चीज है, लेकिन आपके हस्बैंड आपके कहते हैं आपको जॉब करना पड़ेगा, वो गलत है। दूसरी बात, आपके हस्बैंड आपके रसोई में आपकी हेल्प कर रहे हैं अपनी मर्जी से, वो अच्छी बात है। आप कह रहे हैं आपको तो आज रसोई खाना बनाने को, ये चीज है। अब अगर अगर जैसे मान लीजिए कोई हस्बैंड चाहता है कि मेरी वाइफ जॉब करे और तुम जॉब करो, अपना काम कर सकते ना। देखिए दो काम है, एक घर का काम, एक बाहर। मैं तो उन लोगों से कह रहा हूँ, केवल उन लोगों से कह रहा हूँ जो ये चाहते हैं कि वाइफ जॉब भी करे, शाम को घर आए जॉब करके, और वो लोग हस्बैंड लोग घर पे बैठे और वो एक गिलास पानी उठा के नहीं पिएगा। मैं उन लोगों से कह रहा हूँ, नहीं मैं नहीं कह रहा हूँ, मैंने कहा ही नहीं, मैंने कहा जिसकी है उसकी वैरायटी तो आपको बहुत मिल जाएगी, मैं उसकी बात नहीं कर रहा, वैरायटी तो बहुत है, लेकिन मैं उन लोगों की बात कर रहा हूँ स्पेशली जो मेरा पॉइंट आउट वही है कि जो चाहते हैं कि वाइफ तो जॉब करे, लेकिन जब वो जॉब से घर आएंगे तो घर में एक कप चाय भी बनाएंगे, एक गिलास पानी उठा के पिएंगे। वाइफ जो आई है जॉब करके वो सारा काम करते हैं, वो नहीं चाहते, वो उन लोगों के लिए, बाकी लोगों के लिए भाई देखो ऑपरेशन हर जगह चाहिए, ऑपरेशन तो मिलता कैसे कैसे तुम कैसे तुम क्या चाहते हो? हाँ ये सही है, ये पॉइंट सही है, ऐसा होना चाहिए, ये पॉइंट सही है।
अक्सर आप ये कह रहे हो आज भी ऐसे भी है, जैसे आप मैं जॉब नहीं भी करती थी तब भी मेरे हस्बैंड मुझसे ये कह रहे थे कि अगर तुम्हें लगता है तो बेबी रख लो, तुम्हें लगता है तो तुम खाना बनाने वाली भी रख लो, तुम्हें अगर अनकंफर्टेबल किसी भी चीज में हो रहा है,
ये कॉम्प्रोमाइज नहीं है,
ये उनका है कि तुम्हें नहीं, तुम्हें तुमसे नहीं मैनेज हो रहा है, तुम्हारे पेट तुम्हें लग रहा है,
अपनी तरफ से सपोर्ट देना चाहिए अपनी बात, सपोर्ट भी बोलना चाहिए, हम तुम्हारे लिए हेल्प करने तैयार हैं, ये नहीं कहना चाहिए अरे चाय बना के लाओ चलो अब तुम मेरे काम करके आए हो, तो काम करके क्यों नहीं होंगे,
कोई नहीं बनाते सर, सब तुम जब साथ में काम कर रहा है तो हर आदमी सुबह चाय बना रहा है, आप दिल्ली में जाओ
तुम ऐसे नहीं हो,
अरे मैं अपनी को कह नहीं रहा हूँ, मैं तो अपनी बात नहीं कर रहा हूँ, मैं तो अपनी नहीं कर रहा, मैं तो आपकी जनरल जो आपने मैं केवल उस बात पे कह रहा हूँ जो आपने एक बार कही थी,
चेंज द टॉपिक, चेंज द टॉपिक, चलो
ठीक है, ये है
भाइयों मुझे लगता है वो आ गए हैं, देख ले।
अब तो ज्यादा होगा पड़ेगा।
Excuse me, sir.
Good afternoon, all the remote centers. This is the third session of the fourth day, and we have invited again Dr. Umesh Tiwari. Yesterday he was speaking on the detectors and other thing. I hope you might have enjoyed the teaching and some demonstration also. Today we will discuss about the optical fiber amplifiers. Optical fiber amplifiers, there are varieties of optical fiber amplifiers. So he will categorize according to his work and speak on the topic. So now I request Dr. Umesh Tiwari to start the session, and the students available in the studio of the ME classes, you are most welcome to ask the question wherever it needed. Though I have not taught to you the optical fiber amplifier, but in very near future will teach you. But light emitting diode detectors you have gone through, so you can interact with Dr. Tiwari.
Thank you, sir. Very good afternoon. Thanks to Professor Achan for nice introduction. So, the title of the today talk is Optical Fiber Amplifiers, Performance and Issues. So, with that, the outline of this lecture is I have to discuss about the erbium root fiber amplifiers, Raman amplifiers, study and performance analysis of the Raman EDFA hybrid amplifiers, because we know like EDFA and Raman, they have their own advantage and disadvantage. So if we combine, so to get their best performance, right? And then I have also worked on a few things on the EDFA SOA hybrid amplifier for the broadband amplification, because some of the amplifiers, they have their limitations, like they cannot go beyond after certain bandwidths. So like if we combine SOA with the EDFA, so we can get a even broader bandwidth. And then I have to summarize the talk. So with that, like because this for the remote centers, basically, particularly this particular graph I have already shown yesterday also, but now I have today some of the students in the studio also, so then it is benefited to them also to show this graph for the attenuation. It is called the attenuation plot with the wavelength for the optical fiber, like what is the loss of the optical fiber if we are operating at a different wavelengths, right? So the first, as you can see, the top of this height of this diagram, so this is called the first window, right? The first window is at the 850 nanometer. Okay, so we know like the fiber is having very high loss in 850 nanometer windows, right? And then dispersion was also quite high, right? Then the things will be was shifted to the second window, right, at 1310. Okay, so the 1310 we are getting zero dispersion, right, but loss is still high. Okay, then the communication is shifted to 1550. Okay, so at 1550 the loss is very low, around 0.2 dB per kilometer for the SMF28 or G652 fiber. Okay, that is SMF28, or you can say standard single mode fiber, and as for ITU norms, it is also called the G652 fiber. Okay, so basically in 1550 nanometer wavelength window, you see it is also called the C band. Okay, it is called the conventional band or communication band. Okay, and the thing is, the sources and the amplifiers and the receivers are quite easily available at 1550 nanometer band wavelength window, right? So that is why we are now communication is taking place at this wavelength window. So the thing is, like, I have to discuss all the amplification at, particularly I have to concentrate on this window, 1550 nanometer wavelength window. Okay, so this is a very brief of typical optical communication system, what comprises of. So that we have laser diodes, they are also called the transmitters, and because I have denoted here lambda 1, lambda 2 and lambda n, so that they denotes different channels, okay, or different wavelengths. So the different wavelengths consist different channels. Okay, so and then we have a mux, and it is a optical or fiber optical mux, okay, in line. Then we have a amplifier, and as you can see on the figure, like, we have three amplifiers at three different locations. Okay, so as according to their location, they have denoted with the different nomenclatures. Like the amplifier which is very near to the transmitter, it is called the booster amplifier. Okay, because it is boosting the power basically, because initially in the link, when we are transmitting the optical power, it is quite high, so that is why we need a booster, so it can boost the optical power, so it can travel longer distances. Okay, and then we have a transmitting fiber, it's communication fiber. Then we have a again amplifier. So if I have a very long link, let's say 500 kilometer, 1000 kilometer, okay, so this amplifier is called the inline amplifier, which is amplifying the signal in between the link. Okay, and then we have a DCF, because as we all know, there is a dispersion. Okay, dispersion in the standard single mode fiber. And what is the dispersion? Dispersion is basically subroutine of the pulses. Okay, due to the so many reasons. Okay, because we have a finite width of the sources. Okay, then so that affects the material dispersion. Okay, and then we have a waveguide dispersion. So both combined together, and they are giving the dispersion. Okay, so then dispersion is around, for the SMF28 is minus 17 picosecond per kilometer nanometer. Okay, so this much of dispersion is there. So if we talk of long haul communication or for the longer span, so dispersion become quite high. Okay, so then dispersion affects basically your bandwidth. Okay, so there is a overlapping of the pulses and crosstalk, and all those things are coming in the picture if the dispersion is high. Okay, so then we have a DCF. Another thing is the DCF fiber is having a more losses as compared to the single mode fiber. Okay, so yeah, let's say if we have so longer span length, even 100 kilometers, so then the dispersion becomes the minus 1700. So then DCF basically having quite high dispersion coefficient. Okay, negative. So then it compensating. So then for 100 kilometer also you need to have only 10-15 kilometer according to the requirement. One can put and design the DCF fibers. So DCF is having losses around losses around 0.7 dB or maybe higher. So depending upon what kind of design is. So it is 0.7 dB per kilometer losses. So then again we have a amplifier near to the receiver, and this amplifier is called the pre-amplifier. It is basically deployed to enhance the receiver sensitivity. Okay, because otherwise if you have very low power, so which your receiver is basically what? It is a detector. Okay, so detector cannot detect if the power level is going beyond its detection limit. So then if we amplify the again power, so then it can detect. And then we have demultiplexers which can separate out these channels, and then ultimately we have a receiver. Okay, so this is basically a picture of a optical fiber communication system. So basically these optical fiber communication systems has two major issues: attenuation, as I have already mentioned. So we need amplification at regular interval. So after 70-80 kilometer, then we have a dispersion, so that we can address using the dispersion compensating fiber. So if you see the traditional optical communication system, so they are also called the 3R. They are called the 3R because there we are people used optical to electrical, electrical to optical. Okay, so then they are called the retiming, reshaping, regeneration. Okay, so they are called the 3R generation. So the loss compensation. So then here repeaters we have to put at every 20 to 50 kilometer. Okay, if we are using the 3R or electronics repeaters. Okay, and they have also limited by the so many limitations like bandwidths and all those things, because you know, like electronics amplifiers, they are limited with the RC time constant. So then only one frequency or one particular wavelength you can amplify at a time, right? So if you talk of the DWDM, WDM, UWDM, so then you can't use basically these kind of 3R regenerations. And another thing is like if you tomorrow upgrading your existing communication system again, so then you have to put another new amplifiers if you are using the electronics amplifiers. But if we are using the optical amplifier system, EDFA or maybe some other amplifier, so you don't worry about all these issues, because here EDFA amplifying the signal in optical domain. Okay, the pulse is coming in the same way it is amplifying the optical pulses. So you are getting, so you don't worry about the bandwidth, you don't worry about the what is the bit format, whether it is RZ or NRZ or DRZ, whatever bit format people are using, they can be amplified as it is, right? So this is like some of the introductory part. So you can see here like in a more schematic way. So then we have a optical signal, then we have a WDM coupler, so which is combining the pump as well as the signal wavelength at 1550, right? And the pump wavelength is at 980 or maybe the 1480. So the erbium has a broad emission around 1550, where silica optical fiber have minimum loss, right? And the principle is by using the population inversion of erbium doped silica fiber, it behave as a optical amplifiers. So after combining the pump and the signal, it is going to the active fiber. The fiber is pumped and erbium ions, they are going to the excited state. While coming down, they have some metastable state, which I will explain you in the next slide. And then a fresh signal from the incoming input signal, it is stimulating the excited state erbium ions, and when they are coming down, they are transferring the energy to the weak signal, and you are getting amplified signal at the output. So here, from here also it is quite nicely represented. So it's another way of the representation of the principle of an ADFA. So you can see here, like we have a input signal, then we have a isolator. Isolator is a device which is allowed to propagate the optical signal in one direction. Okay, and then we have a WDM which is combining the pump and the signal. So you can see here in the input port, here we have a quite high pump power and the low input signal power. So when the pump is pumping the erbium doped fiber, it is absorbed in the medium, right? And it is giving a fresh signal of 1550. So here you can see the 980 nanometer signal is low, and the 1550 you are getting amplified. Okay, so then again we have a isolator at the output, so that the pump backward pump cannot enter to the your erbium doped fiber, and it cannot destabilized. And then we have output, so then power exchange between pump and data signal. So this is like how the optical EDFA basically works. Then there are some of the comparison, like behavior of EDFA for the gain saturation. So this I may cover later. So because here it is better to explain this slide, where you can see what is the principle of EDFA. So this is the basically called the energy level diagram of erbium doped ions. Okay, so here you can see we have a two option of the pumping, like 1480 nanometer and 980 nanometer. So if you have gone through the lasers, okay, so if you have studied the laser, so you know this possesses a 3-level laser system if we are using the 980 nanometer pump. So the erbium ions from the ground state, it is depicted by E1, right? When we are pumping, they are going to the level E3, okay, and because at the excited state, the lifetime of the erbium ions are very small, okay, so they are coming down to the metastable state. Okay, the second level E2 is called the metastable state, where the ions, they are stayed for the longer time. Around the time for their lifetime at this stage is around 10 to 13 milliseconds. So quite high longer time, right, for the erbium for relaxing here. And when a signal from the same frequency, you can say, or same wavelength, or which is having the same energy difference, because we are talking in 1550, so the signal which we want to amplify it also 1550. So when it is coming and it is striking the excited state erbium ion, so it is getting the energy from the excited state erbium ion, and they are coming down to the ground state, and it is releasing a fresh signal of 1550. Okay, and because erbium is having quite broad spectrum, right, quite broad spectrum, so it is not a single wavelength or single frequency is amplified. We are getting quite broad bandwidth, and it is around 40 nanometer, like from 1520 to 1570 nanometer wavelength bands for the erbium doped ion. Right side you can see it is called the emission and absorption cross section of erbium doped fiber. Okay, so this tells about the ability of an ion to emit and absorb the light. Okay, so this is giving the ability of the erbium ions, how it is absorbing and emitting light with respect to the wavelength. So you can see we have a very strong absorption at 1500 around also, okay, and emission also. But emission spectrum, if you can see in dotted lines, so then it is shifted, quite shifted, right? So that is why we are getting amplification. So from here also, from the this figure also one can explain, because even the pump is low, but we can get some of the amplification due to this emission spectrum is higher than the absorption spectrum. So you can see like pump at 980 used to create a population inversion between E2 and E1 level, and stimulated emission between E2 and E1 leads to the amplification. So these are some of the basic equations, like to model the amplifier. So under steady state population concentrations, they are called the N2. N2 is the population inversion at the higher state, and the N1 is at the ground state, and in that same excited or ground state, and they can be written as their ion concentration N2 and N1 with respect to R, phi and Z. So this is like those who are interested in doing the simulation, maybe they can use this kind of equation, and these equations were taken from the different references which I have given in the next slide. So where PER is the emission ion concentration, WA and WE are the total absorption rate from the ground state and the total emission rate. So here you can see pump and signal power evaluation equations is given as it is taken from the Pedersen. So this paper is highly cited, and you can see also the everybody in the world, those who have done the simulation in the erbium doped fiber amplifiers, they have referred this paper. It's a very good paper. So then using these equations, dP by dZ and dPPS by dZ, they are also called the coupled equation. Okay, they are called the coupled equations because they have to solve simultaneously. They cannot solve independently, because in both the equations you can find out some of the parameters are common. Okay, so that is why you have to solve each other, like because they are giving the dependence of bump with respect to length or Z, and the propagation of the signal with respect to Z, and the gamma E with respect to frequency and Z, and gamma A with respect to frequency and Z are the evaluated from the cross sections, okay, and overall overlap integral between signal and population concentration, because there is a overlap, because in silica the erbium ions are doped in the core of the silica fiber, okay. So then one has to find out what is the overlap between for the fundamental mode of the optical signal and the erbium ions. So there must be first estimated, and then one has to do the simulation. So gamma A can be calculated like this 2 pi sigma A. Sigma is the absorption cross section, n1 is the concentration in the your ground state, and then IV is the integral. So this kind like this you can solve the some of the simulation, or you can do the simulation. Then one has, by solving these equations, then you have to find out the gain and the noise figure. So gain can calculated PS nu s L with respect to L, like it is basically P out by P in, you can say, okay, P out by P in, because PS L is the after the length, and PS at 0 at the input. So P out by P in is the gain. So G of nu s, like nu s, why it is given, because it is depending upon the wavelength, because the gain is different at different wavelength, okay, the gain is different at different wavelength. And the noise figure is the ratio of the signal to noise at the input and the signal to noise ratio at the output. So one can find the noise figure. So noise figure is related with the gain and forward ASE spectral density. So this is like one has to calculate the ASE power and the gain, and you have to find out the noise figure. Practical application, like for practically, like we have already fabricated and designed this kind of amplifier, so then we have measured the noise figure experimentally also. So then if the above formula is to calculate or estimate the noise figure theoretically. If you have all these values of every parameter, so then you can calculate theoretically. And if you have experimentally, so by using a optical spectrum analyzer, you are having the some pump, some length of the optical this erbium fiber, you can pump it, you can see the response at the OSA, and then you can measure. So people have calculated N out is the noise of the at the power of the output power of the signal at the noise level, and then G is the gain, N in is the power of the input signal at the noise level. H nu, H you know it is a Planck constant, nu is the C by lambda, at what wavelength you are calculating the noise figure. B is the bandwidth of the optical spectrum analyzer, at what bandwidth you are measuring. G is the gain. So like that you can calculate. So that we have already calculated by using both like now to simulate these kind of amplifier. There are so many softwares available commercially, like OptiSystem, OrSoft, OptiSim, and many more. So like you can do the simulation on using the OrSoft, this kind of software as well. But what we have done, like we have also compared, because you see sometimes we don't know like whether softwares they are working absolutely fine or not. So we have done the calculation using MATLAB code, like we have done the programming, and then we have calculated the gain with length, and then the same we have done using the OptiSystem. So there you can see in the figure here. So then their response are coming quite close. Okay, so they have a very good agreement. Okay, then this is the simulated gain and noise figure. So in the lower graph, so because here we have calculated the gain, okay, at a particular power at particular wavelength, but here in the lower graph, as you can see, we have taken 150 milliwatt of pump power, and the length of the EDF was the 12 meter. So here we have simulated at different input powers, like minus 5 dBm, minus 10 dBm, minus 15 dBm, and noise figure is also at 3 different wavelengths. So as you can see here, the gain at the lower input signal power is not flattened, okay, and that is due to what? That is due to the saturation effect, because at high input signal power, as you can see here at the minus 5 dBm input power, because input power is quite high, so the gain at each wavelength is coming quite flat, okay. because of the saturation effect. Okay, because if input power is high, so what happen if input power is high? So there is no more erbium ions are available at the excited state which can stimulate the erbium ions. Okay, because we have now more and more signal photons at the higher level. Okay, so and all the erbium ions, they are already stimulated, okay, by the available input photons. So now each wavelength, the gain is coming same, but at the input signal, if you see the lower power, okay, so at the lower input power there is not sufficient number of input photons available, so then still the gain is according to the erbium emission spectrum, as you have already seen here also. Because if you can see this figure, so there is a peak, okay, there is a peak at around 1535 nanometer wavelength region. Okay, so the gain is not flat automatically. Okay, so there is some desirable characteristics of this optical EDFA. One of them is we must have flat gain. Okay, what does it mean? All the wavelengths should experience equal gain. Okay, otherwise it will affect your bit error rate, right? Why? Because at, let's say, at some particular wavelength you are experiencing more gain, at some wavelength you are experiencing a very less gain. So because it is not a single unit of the amplifier, because there is number of cascaded amplifiers deployed in the link. Okay, so what happen when it is going to the next stage and next stage? So the signal which is having the high gain at the first unit, when it is going to second unit, it amplify more. Again in the next stage it is amplifying more. So when it is going to the receiver, so what will happen? The wavelengths or the channel which is experiencing high gain, they become one, and the channels which are experiencing very low gain, they become the at the noise level, or they may be the below threshold, so they become 0. So ultimately your BE are going to be affected. That is why the gain flattening is important. So for the gain flattening there are so many ways, like people have proposed, and they have used gain flattening filter by using the fiber break grating, using the long period grating. So these are like and some other techniques also people have used for the gain flattening of erbium dot fiber amplifier. Okay, then another issue with this EDFA is polarization dependent gain. Okay, so what is the polarization dependent gain? The variation of the gain of the amplifier with the, if the state of the polarization of the input signal is changed. Okay, because you know, like optical fiber is not a circular symmetry. Okay, it is not a perfectly circular. So because it is not perfectly circular, so there is a, you know, like there is a linearly polarized mode. Okay, so they have their polarization at 45 degree. So the thing is, when the light is propagating through the optical fiber, so after certain length the polarization is going to change. Okay, so then one should know like how much the change in the gain, or how the gain is affecting with the changing the polarization. Because in EDFA there is a signal and there is a ASE. ASE is the amplified spontaneous emission. Okay, so ASE is the amplified spontaneous emission. So the ASE is basically unpolarized and the signal is polarized. Okay, so due to that there is a polarization dependent gain, and it is due to the polarization hole burning. Polarization hole burning is that the unpolarized ASE is amplified more as compared to the signal. Okay, so due to that the gain become different as if you compare to the unpolarized. So the PDZ is calculated by this formula, the PDZ in dB basically. So 10 log of P max by P min. So like we have measured, and it coming, the PDZ is around 0.2 dB at -5 dBm input power and 150 milliwatt of pump power. So this is basically experimental results. So this is not like this is our own results. Like we have after making the amplifier, we have measured by our own. So the thing is like PDC one can measure by using the PMD analyzer. It's the name of the equipment, where it consists of different portion like polarimeter, polarization scrambler, polarization controller, right? So then you have to change the state of polarization, or you can scramble the state of polarization of the your input incoming input signal, and then scrambled polarization is giving to the EDFA, and then you have measured the output in the polarimeter. So you can see when the polarization is minimum, what is the gain, and when the polarization is maximum, what is the gain. So in that way you can calculate the maximum power and minimum power, and then you can calculate the average of the PDC. Okay. So then this is basically how we have measured the gain and noise figure using the this is called the basically technique to measure the gain and noise figure. This is called the so just a minute. Yeah. So here you can see the output and the input. So I have explained here. Yeah, so N out G into N in and H nu B into G. So if you see these figures, so they have shown the input signal as well as the output signal. They are called the extrapolation method basically. So you see here. So we have measured the N out is measured like this. We have measured this portion and this portion to measure the N out, and we have taken the average, right? And N in have been calculated using here from the input source spontaneous noise. So this is the source input power at the noise level. So in that way this was calculated, which is given in the I have explained earlier. Then we have also this is also one of the representation, like so just to see in a different way, just to see this extrapolation. And here like this is the basically we have made erbium dot fiber amplifier. What are the different components? So this is actual schematic. So what are the different components being used? So tap coupler, isolator. Tap coupler we have used for the automatic gain control. Isolator is just to see so that the input signal cannot flow in the, it not can go to the transmitter. Then WDM, then erbium dot fiber. Again we are using the WDM at the output also to separate if any residual pump is there, like unutilized, if it is not absorbed completely, or if the fiber length is not sufficient. Then we have again isolator at the output, it can cutting off the pump, right? And then tap coupler. So by using these two tap coupler, one can make the automatic gain control, like if the gain is changing, so we are tapping some percentage of the input and output, so accordingly the system can put more pump so that the gain should be equal. Okay, so to make the gain control, this tap coupler have been used. So you can see like what are the different steps to experimentally design a erbium dot fiber amplifier. So first of all, because all these components is not manufactured in India, so we are basically importing from different places. So first of all, you don't know like what is their different parameters, say for example insertion loss, isolation, and all those things with respect to the wavelength. So first of all you have to characterize. After purchasing you have to characterize for each and every components. Otherwise maybe you have designed something else, and when you are going to get the output you are getting different. So first you have to characterize what is the insertion losses and isolation losses, so accordingly you can put the length of the optical fiber and according to the pump power. Okay, then we have also studied the dependence of the gain with the bend radius, because we are making a complete system. So what is the size of the system, so what could be the bend radius? Otherwise with the bending there is a loss. Okay, I don't know how whether you have experienced any time this kind of experimental things like the loss of the optical fiber with respect to the bend. Okay, so there is a bending losses. Then we have so then in our case it was a 5 centimeter. Then we have also optimized our splicing system. Have you used the splicing system to splice to join a fiber? Have you seen? No. So because optical fibers are made of silica glass. Okay, so it is not like copper cable and you can go and then you can fuse with the different techniques. Okay, here it is basically glass. How you can join? Either you have to melt it, right? So by melting and you have to join. So then there are joining system. They are called the splicing. Okay, so they are using the arcing. Okay, and they have electrodes. So by electrode they are providing very high temperature through the electrodes, and then the two fibers very nicely cleaved at the 90 degree, so that they have nicely core to core coupling, and then you have to join them. So but the thing is here SMF fiber and EDF fiber are different, and they have the different mode field diameter. I don't know whether you know the mode field diameter, but if you have a different mode field diameter, so losses are more, okay, between two fibers because of the mismatching of the mode field diameter. So that those things must be optimized before designing amplifier. You should know, so that you can take care of all these losses at the output. And then we have calculated the optimum length by using the software and then other things. So then we have done our experiments, and then we have got basically more than 20 dB gain and less than 5 dB noise figure for our amplifier for input power of minus 5 dBm. So I don't know whether you are aware of dBm. Okay, because I'm using very frequently dBm. Okay, so dBm is basically power. dB is the ratio, but dBm is with respect to the 1 milliwatt. Okay, so it's when we are talking of power, it is a dBm. When we are talking of gain or losses, it is dB. Okay, so so then it was all like this figure was for the single channel characterization. Like single channel is when only one wavelength were present in the spectrum or in the bandwidth of the EDFA, okay, at a time, right? In a whole spectrum, only one wavelength was we have scanned, okay. Like at a time, sometimes it was because we have a tunable laser source, so then sometimes it is at 1525, and then we have scanned in 1 nanometer spacing, so like then 15, 26, 27, 28, and we went up to 1565. Okay, so like that. So we have calculated the gain and noise figure using those formulas which I have already explained, and then we have done the multi-channel characterization, because you know, like multi-channel characterization is important. Why? Because you don't know when many channels will be present in the system, what could be the behavior of the amplifier's output spectrum. Okay, so because we all are talking of DWDM, WDM. Okay, so in DWDM and WDM there are not a one wavelength. Okay, there are multiple wavelengths. Okay, so we should know like how the amplifier behaves when many channels were present. So this we have done using like we have a different transmitters like at different ITU grid wavelengths. Okay, so we have a complete DFB systems are at 8 wavelengths. Then we have a MUX also, fiber multiplexers, and then these wavelengths combined and then they sent through the EDFA, and then again we have a DMUX, and you know like OSA is also act as a DMUX. Okay, because it is grating based, so then it is separating out all the channels. So then you don't need to put a DMUX at the output. If you put the OSA, you can get all the wavelength at different locations. Okay, so then you can see there is a quite difference, okay, in single channel and multi-channel spectrum. And we have also, these are the wavelengths which is given at the this right side. So they all are at the ITU grid. Okay, because ITU have already defined within a WDM system or DWDM, what are the nomenclature of the wavelength. Okay, so I2U know, like International Telecom Union. Okay, so they have already defined the grid. So these are the different like available. Basically, you can say these are the available wavelength with us. Okay, so that what we have purchased the DFB lasers at these wavelengths. So the thing is only good thing was, fortunately we have purchased in such a way like we have covered whole the spectrum of EDFA, because we have they were started from 1530 and they went up to 1557.36, so it almost covered whole spectrum. So you can see that there is a gain tilt. Okay, there is a gain tilt when we are using the multiple wavelength in the spectrum, and also we have estimated how the gain curve is behaving if there is a 4 channel present, 6 channel, 5 channel, 7 channel, 8 channel, different channels. So the thing is here, because of the spectral hole burning, because when there is only one wavelength is present in the system, so you can see the only one channel is eating all the energy from the whole spectrum. Okay, but when there are more than one channels or more than one wavelength is present, so then there is a localized effect. Okay, so then they are eating the energy from their local areas. Okay, so that creates the hole in the erbium ions. Okay, so due to that, the gain is not flat. Okay, gain is not flat, and we are getting different behavior as compared to the single channel, because in single channel you have already seen the gain is completely flat, but in case of multi-channel gain is not flat. So basically this kind of experimental things were carried out to just to mimic or to predict what could be the behavior of the gain spectrum of the EDFA if tomorrow 16 channels are present or maybe 32 channels are present. So the thing is like it is very difficult to purchase that much of system, right? It become very quite expensive. So one cannot afford, like even 8 channels system was more than 40 lakhs. So like if we go for 16 channel or maybe more, so then it is quite expensive. So then you cannot get those kind of system to characterize, but at least by some experimental simulation, you can say these are the experimental simulations, so that by doing these kind of experiments one can see like what is the behavior, right? And then we have also done this polarization dependent gain for the multi-channel. So, and these are the then we have done some of the characterization of these developed amplifiers at the different data rates also, like that we have done at 2.5 Gbps at Tejas Network Bangalore, because they are the telecom industry and they were the partner of our in this project. So then we have characterized for the eye diagram, bit error rate, all those things. So you can see here the first eye diagram is for the transmitter at 2.5 Gbps. So you can see the eyes are very good, they are open, and the right side the eye is for the EDFA. So only the difference is only because the ASE noise, there is a broad on the height of the eye. Okay, so there is a broadening, and here because this is only the laser or transmitter, so there is not a broadening. Okay, and again in the lower graph you can see it is a measurement of the BER for the transmitter, the black response, and then the red, yeah, the right side the I is for the EDFA. Okay, so you can see the red graph. The red graph is the BER for the transmitter, EDFA, and 140 kilometer link. Okay, so the bit error rate is very good, around 1.3 into 10 to the minus 9 at the power level of minus 30.75 dBm. Okay, so this kind of BER you can receive. So what is the BER, standard BER? You know, minus 9, right? So this kind of BER is up to the acceptable limit. Then this is the fabricated amplifiers, like we have fabricated at the IIT Delhi in collaboration with Tejas Network Bangalore and Optic Wave Photonics Hyderabad. So this is the inside view, and this is the whole this thing. So these are the some of the specifications. So even if somebody is going to purchase the EDFA, they should know what is the specifications, how much power you needed, what kind of gain you are required, right? What is the noise figure. So these are the some of the specifications we have also brought down, and then we have given to the industry, and now the industry is manufacturing this kind of amplifier, and they have already supplied to many telecom giants like Reliance and Bharti Telecom, and they have deployed these kind of amplifiers. So the thing is this, we have developed these amplifiers, so it helps to reduce the cost, right? Now earlier this EDFA was available at around the cost of 2.5 lakhs or something, but now it is available in India also, and its cost is less than 1 lakhs. Okay, so development of the technology in country, like not only the availability, but it is also bring down the cost in the market. Okay, so it is helping in two ways. Okay, then we have also designed and developed mid-stage atom fiber amplifier. Mid-stage amplifier is needed when we need to amplify the signal in a midway, like in the optical communication system. There are many components, or you can say many kind of instrument people are using, like optical airdrop multiplexers. Okay, then dispersion compensator, VOA. It is a variable optical attenuator to achieve the variable gains. Okay, so now there is a two stage, like there is a one amplifier, in between there is a either AODM or dispersion compensator or VOA. So, and then another stage, again we have a one amplifier. So you have to optimize all the parameters to get the best performance. So this is also we have made and fabricated. So here you can see this characterization of the mid-stage access EDFA for the single channel, and then there is a characterization of the mid-stage EDFA for the multi-channel, and these are the gain and noise figure characterization. Then gain flattening, you know, there is a high gain at particular wavelength locations. So if you have this kind of graph, so then you have to design your filter in such a way you cannot get a negative dip with the same bandwidth. So due to that you can get a gain flattened. So this kind of in the lower figure, it is a schematic of the mid-stage access EDFA with gain flattening filter. Okay, so these are the just schematic representation. Then comes to the Raman amplifier. Okay, so you know the Raman amplifier is based on the Raman effect. Okay, so Raman effect is based on Raman scattering. Okay, but Raman amplifier is based on the stimulated Raman scattering. It is called the stimulated Raman scattering. Okay, so the energy by energy level diagram, you can depict the stimulated Raman scattering. So here, when a silica molecule is interacting with the pump photon, okay, so due to the silica molecules, they are going from the vibrational ground state to the virtual excited state. Okay, and when they are coming down to the virtual excited state to the vibrational ground state, they are emitting a Stokes photon. Okay, and the Stokes photons, they are emitting both Stokes as well anti-Stokes. Okay, but the probability of the Stokes photons is much higher than the anti-Stokes. Okay, so when a coming signal with the same frequency of the Stokes photons, okay, is coming to the virtual energy states, okay, so they are getting the energy from the Stokes photons and gets amplified. So this process is called the stimulated Raman scattering. Raman scattering is just simple because if there is no signal, okay, it is just the Raman scattering, because you have just pumped your medium. A medium is what? Medium is optical fiber. Okay, and in optical fiber there are silica molecules are available, and you are pumping with a pump photon. Pump photon is nothing but a light with some particular wavelength. So the thing is, only it is simple to say, but it is, the process is very difficult because it is a non-linear process. Okay, this is a non-linear process because to convert a pump energy to the signal energy, or from a pump photons to the signal photons, they are transferring the energy after a L effective. There is a effective length, like they are taking hundreds of kilometers. Okay, they are taking hundreds of kilometers to convert a pump to transferring the energy from pump photons to the signal photons. Okay, so this process is a non-linear process, but the thing is, if you use a different kind of fiber where the non-linear coefficient is more, the fiber are available which have a very high non-linear coefficient, so then you can, even using a smaller length, you can get this effect very prominently. Okay, and you get a very good Raman gain. Okay, so you can see here, this is called the Raman gain curve, and it is quite broader. Okay, so the thing is, Raman gain is available in all the wavelengths, not only the C band, L band, S band. You know all these bands, right? I hope, right? So Raman gain is available in all the bands, but EDFA gain is available on the C band. Reason, you know, because EDFA has its own characteristics. Okay, it has emission only at the particular wavelength, but in Raman case, Raman gain is depending upon the two things. One is the medium, another is the pump wavelength. Okay, because whatever pump wavelength you used, right, you get accordingly the Stokes shift. Okay, and Stokes shift is 100 nanometer apart. It is around 13.5 gigahertz, 13.5 terahertz. Okay, and if you convert 13.5 terahertz into the frequency, into the wavelength, it is coming 100 nanometer. So to get the amplification at 1550, so the Raman pump should be at the 1450. Okay, so one has to use the 1450 nanometer wavelength Raman pump to get the peak gain at the 1550. Okay, and this Raman curve is provided and it is taken from the literature, and it is at the Raman, the pump wavelength is at the 1 micron. Okay, so you can see here, these are the basically some of the equations, basic equations to simulate the Raman pump, Raman gain. So here also they are called the coupled equations. So dpps by dz is basically depend upon the alpha s. Alpha is the absorption coefficient of the signal, then ps is the pump signal power, gs is the Raman gain coefficient, pp and ps is the pump power and signal power, plus minus dp by dz. Okay, so plus minus indicate whether you are using the backward pumping or forward pumping. Okay, so plus is forward pumping. Forward pumping is when the pump and signal both they are propagating in the same direction. Okay, backward pumping is when the signal and pump both are propagating in a different opposite direction. Okay, so that is called the backward pumping. So here again dpp by dz is the alpha p. Alpha p is the coefficient of attenuation coefficient at the pump wavelength. Okay, in the fiber, pp is the pump power, gp is the Raman gain coefficient at the pump, and pp and ps is the pump power and signal power. Only the thing is, you have to see here, gs is the gr by kappa a effective. Okay, so gs is higher when effective area is very small. Okay, so that is why people are preferred to use the fiber with the very small effective area. Okay, so then, so that you can get very high Raman gain coefficient, and if the Raman gain coefficient is high, you will get a high Raman pump power. Okay, So these are the some the configuration of Raman amplifier. So you have again these kind of devices like isolator, WDM at different wavelength. The earlier components used for the EDFA, they were at the 1550 nanometer wavelength. Okay, here the components we are using at the 1450 nanometer wavelength. Another thing is these devices we are using for the high power, because Raman pump power is very high. Okay, it is around 1 watt. Okay, it is around 1 watt we have used, because you know Raman this Raman effect or Raman scattering. For Raman scattering we need to have a very high power, because if you have studied the nonlinear effects, so nonlinearity, for nonlinear we need to have a very high intensity. Okay, so intensity is basically P by effective. So if the power is high, the effective area of the fiber is small, so you can get a very high intensity. So due to high intensity you can get a very good nonlinear effects. Okay, so considering all those things, now you can see here, like here we have used backward pumping. Why? Because in Raman particularly people prefer the backward pumping, because Raman amplifier is used to maintain the signal level in the optical link. It is not used to boost or suddenly amplify the signal. Like it is not like you have put the 1 milliwatt and using Raman you can get a 100 milliwatt. Okay, or whatever, 30 milliwatt, 20 milliwatt, right? So it's not the use of Raman amplifier. What Raman amplifier does, if you put a 1 milliwatt at the output also, it is maintaining the 1 milliwatt. Okay, so at the output also you can get 1 milliwatt. So it is basically mitigating the attenuation effect of the optical fiber. Okay, so depending on the pump power of the Raman pump. Okay, so here these are the some of the simulation results for the co-directional pumping for the single mode fiber. So you can see here, this is the signal and this is the pump. So here the signal is getting evaluated when it is getting a pump, Raman pump, and then it is dropping down because of pump depletion. Okay, because the pump depletion. So if you are using the co-directional pumping, what will happen at the output, the signal power is going down. Okay, so it won't solve your purpose. Okay, so this simulation was done for this parameter. You can see at the right side, like we have chosen the signal power at minus 40 dBm, wavelength is 1550, pump power 30 dBm. So then lambda p is the pump wavelength is 1450, like that. Then if you are using the backward pumping, okay, contradirectional, that is also called the contradirectional pumping. So you can see the first, the pump is depleting or pump is reducing due to the attenuation of the optical fiber. Okay, because it is decreasing linearly, but here the pump is not decreasing linearly. Okay, but in the contradirectional pumping, the pump is decreasing linearly due to the attenuation coefficient of the optical fiber, and the signal is getting amplified when the pump power is above threshold. Okay, so at the output you can see, at the output if you are putting backward pumping, so at the output you are getting a high signal power. That is what we need. Okay, so we are not worrying about what is the signal level at the middle or at the beginning, but we are more concerned about the what is the signal level at the output at the receiver end. So we are getting a very good output. So the Raman gain getting evolved when the pump power is above threshold. Okay, so these are the some of the comparison between the co-directional pumping, contradirectional pumping. Okay, then we have worked on the DCF based Raman amplifier. Okay, DCF based Raman amplifier. Why? Because if you are using the DCF, because I have already mentioned, Raman gain is more in the where the nonlinear coefficient is high. Okay, so DCF fibers, they are very small effective area and they have a high nonlinear coefficient. So here if we use the DCF, So we can solve the two purposes. Okay, what are the two purpose? We can get the loss compensation as well as the dispersion compensation. Okay, because if you are using the DCF, so dispersion also can be compensated and loss can be also compensated by using the Raman gain. Okay, so that is why we have chosen the DCF, and we have pumped with the same 1545 nanometer pump, and you can see here the gain and noise figure for the DCF based Raman amplifier. These are the some of the experimental photographs like we have performed in the laboratory for this Raman amplifier. So this is the fiber, Raman fiber. Basically the lower one is the Raman pump from Kyopsis. It is 1 watt of it is giving the 1 watt of Raman pump power. Okay, so and these are this is the below is the this Raman box. So these are the experimental results basically, right? Those are the simulated results, but here you can see in real scenario, we are measuring the Raman pump like on and off. Okay, so can you guess what is the on and off gain? Because in case of EDFA, we were talking about the gain only, right? P out by P in. Okay, but here we have mentioned the G of on off. Okay, what is the on off like? So on off is basically we are measuring both input as well as output when the pump is on and pump is off. So we have put a link of let's say 100 kilometer or 25 kilometer, and we have put some input signal at 1550, and we have measured the output. At the output we have first measured the what is the signal power. Okay, what is the signal power when the Raman pump is at the off stage. Okay, so after 25 kilometer, if the loss is 0.2 dB, okay, so you can see like your loss is how much in dB. So it is around 5 dB or so. Okay, so then after that, what you have to do, the same pump signal power, you have to measure the output when the Raman pump is on. So in that way one has to calculate the on off Raman gain, because ultimately I have already mentioned the we have to maintain the signal level, okay, at the output. So here you can see these three different graphs we have plotted at the three different pump power. Like when the Raman pump power is at 350 milliwatt, so you can see the gain is very low. Then when the Raman pump is 500 milliwatt, gain is again around 8 dB. When the pump power was 750 milliwatt, the gain is the maximum gain or the peak gain at 1550 around 14 dB. So, and these are the noise figures. So noise figure, I don't know whether you are aware of the noise figure in EDFA. So do you know like what is the quantum limit for noise figure in EDFA? So you cannot go beyond 3 dB, okay, if you are using the EDFA. Okay, that is one of the disadvantages of the EDFA, because it's a quantum limit. Okay, due to if you see the books, then you can understand it. Yesterday, because I have already explained, so today I'm not going to explain it. But in Raman, noise figure is even you can get less than 3 dB. Okay, because there is no ASE. In EDFA, there is a noise figure, high noise figure due to the amplified spontaneous emission. Okay, due to the erbium ions, they are also coming down to the ground state spontaneously. Okay, not due to the stimulation. Okay, so that creates high noise. Okay, but in Raman there is no ASE. Okay, so then we have also performed some of the experiments for the Raman amplifier using the different techniques. Like we have used the OTDR. Okay, optical time domain reflectometer. People are using to detect the crack and in the link and breakage, bending, all those things, right? But here we have used for the different purposes. So then you can see at different pump power. This was theoretically calculated Raman gain, the red line. The blue is the Raman gain experimentally. You can also see there is a lot of noise is coming with respect to the link, because of it is a reflected light. Okay, it is just reflection because OTDR is getting the reflecting light. So this is the 3 milliwatt, then 500 milliwatt, and then 700 milliwatt. So only the thing is you can see the behavior of these curves. So they are going high and high with respect to the different Raman pump power. Okay. So another important issue with the Raman curve is it is all again it is not flat, and another thing is you cannot get flat gain in case of Raman amplifier by using any kind of filters. Okay, gain flattening filters, because its spectrum is quite broad. Okay, around 100 nanometer or so. So no filter is available with the 100 nanometer. So what we have to do, the people are using doing the Raman gain flattening by using multiple pump. Okay, so multiple pump at different wavelength. Okay, so you can see at different wavelengths. So then all the you can, if you cut off here, right, so you can see like we can get a flat gain. Okay, so the flat gain can be achieved by using the multiple pumping. Okay, so these are the initial profile with when the differential gain is 2.5 2.1 dB, and optimized profile differential gain is 1 dB. So these are the some of the calculations for when people have used these three different Raman pump at 1420, 1450, 1480. So then the peak gain is going at a different wavelengths, because I have already mentioned stoke is created at 100 nanometer apart. Okay, Aji बताइए कोई problem है? Okay, so then after that actually I'm also going to just give you a brief of hybrid amplifier. Okay, so hybrid amplifier, like we have also worked on these hybrid amplifier, and depending upon their different deployment, like in some of the configuration the EDFA is the first stage, Raman is at the second stage, then Raman is the first, EDFA is the second stage. So then accordingly we have then estimated their performance, and we have carried out different so many experiments, and then you can see also they have offer several advantages, like we can get high gain, low noise figure, high pump efficiency if we are using hybrid amplifier. Okay, then as we have already mentioned, like we can compensate both dispersion as well as losses. Okay, DCF has higher Raman gain coefficient, amplification band expansion easily achieved, like you can also enhance the bandwidth. Okay, because Raman is having a quite high bandwidth, and if you add the EDFA, so we can get for the higher bandwidth, more bandwidth. Okay, then polarization dependent gain, we have measured signal to noise ratio, and all these parameters have been already evaluated using for these amplifiers. So these are the some of the results I'm going to present. So this is for the hybrid one, so where the EDFA have been pumped after the Raman stage. So you can only the difference you can see here in EDFA case we have been used for 980 nanometer pump. Okay, but here why I have told you, like it is also enhancing the pump efficiency, because the same pump we are using, which we are using for the Raman. Okay, so the Raman pump, first we have pumped this Raman DCF module, and then we have calculated what is the how much the pump were left and it is not utilized by this DCF, and then we have simulated for that much of Raman pump how much length of EDF we required. So accordingly we have simulated, and it comes around 13 meter. So the 13 meter fiber was then pumped by the residual pump of this Raman. So using same pump which were unutilized when we are using only Raman section. So now we are combining both. So you can see here single channel gain. Now this is not the on-off gain. Okay, in case of the EDFA we were getting the on-off, but here now we are getting absolute gain, and you can see we are getting more than around 15 dB, okay, around 14 to 15 dB. And then we have also done the multi-channel characterization for 8 channel, 4 channel. So you can see, and these are the curve without the any gain flattening filter. Okay, we have not used any gain flattening filter. So the highest peak for this multi-channel is coming due to two reasons. One is the because multi-channel there is a spectral hole burning and gain tilt is there. Another thing is Raman is giving the maximum gain at 1555 because the Raman pump is 1455. Okay, that is why you can see here the in this region it is giving much higher gain. Then in the this here this is called the another type of hybrid amplifier type 2. So here what we have done, we have used the EDFA at the first stage, okay, at the input stage. So the thing is the signal is first experiencing the loss, okay, and then it is entering to the Raman section. So you can see because input signal to noise ratio is small in case of this amplifier. Here you can see signal is coming here at the initial stage, signal is quite high, okay, so the noise figure is high, but here you can see the noise figure is smaller in type 2 because input signal is first striking to the EDFA stage and then it is going to Raman. So Raman pump is there and then we are pumping the EDFA. Okay, so this kind of amplifier we have developed, and then we have done polarization dependent gain characterization for all these three amplifier. So in conclusion, you can see there is a trade-off, like which amplifier you have to choose. So then it is depending upon the application. If you need best polarization dependent gain and BER, so one can go for the hybrid one. If somebody need lowest noise figure, so it's hybrid 2 is better, and for the best pump efficiency, hybrid 3 is better. So these things we have already they are available in the literature we have published. Okay, and then next do we have some more time?
Yes, sir, till 4 o'clock.
Okay, till 4 o'clock. So then we have also proposed a new kind of configuration for this hybrid amplifier. So where we have achieved all the better performance, all the enhanced performance. So you can see here EDF is followed by the DCF section and EDF section is co-pumped. Okay, so these are some of the results. We have done the simulation as well as the experiments. So the experiments and simulation both are in a close agreement, and we are getting very high gain for this new Raman EDFA amplifier configurations. So the Raman the gain is about 24 dB, okay, at minus 20 dBm input signal power, then around 16 dB for the minus 10 and around 10 dB for the minus 5 dBm input power. Noise figure is also different at different input signal power. Then we have done the multi-channel characterization, and these are some of the highlights. So we are getting best noise figure and lowest gain ripple. Then experimental and simulator results were in the close agreement. Then polarization dependent gain is smallest in all the three. Like the three I have explained, this is the fourth one. So we are getting best polarization dependent gain in the new configuration. So they were also already published. Then a little bit I need to explain the EDFA SOA hybrid amplifier, because SOA is basically having quite broad bandwidth, right, but its gain is small and it has some of the issues, like it polarization dependent gain is very high, okay, and that is some of the reason, because polarization dependent gain is high in case of the SOA, because the TE and TM components, they have the different polarization dependency. The TE is having the longer more gain and TM component is less gains. So, and they are due to different region because of the anti-reflection coating depending upon the polarizations and some other factors also. So considering those factors, people are not using the SOA for the amplification purpose. Okay, but the SOA is used for the many other purposes like the optical signal processing. Optical signal processing means like for the wavelength conversion, as to make the logic gates, optical logic gates. Okay, and optical signal processing maybe as a counter and other things. Okay, so this is the schematic representation of this SOA. So you can see there is a substrate, okay, and then there is a active layer, and then this metallization, then we are injecting the current, and the both the ends faces were polished to get the anti-reflection coating. And so you can see SOA has some features like they have a small size, but another important feature is if you compared with the other amplifier, so there we have used the optical pumping. Okay, here we are using the electrical pumping. Okay, and we have a very broad spectrum. Okay, then they have very good nonlinear characteristics. So they can be integrated with the other silicon based technology. Okay, then they have diverse range of applications like optical switching, wavelength conversion, logic gates, multiplexers, flip flops. So all this optical signal processing can be performed using the semiconductor optical amplifier. Okay, so these are the like the amplification process, right? So basically it is due to the recombination process of electron hole pair. Okay, so then you see all you are from the electronics background, so you know like semiconductor have a balance and conduction band. These are very trivial things. So and at thermal equilibrium, balance band has a higher population. Okay, then under population inversion condition, conduction band will have a higher population because we are sending the electrons to the conduction band. So due to the population inversion achieved by forward p-n junction. Okay, so the Raman this gain will be achieved through the electron hole pair. Okay, recombination process. So these are the some of the limitation advantages that I have already mentioned. So then I am not going to discuss. You'll get the slides, so you can go through. Okay, these are the I wanted to show you the spectrums. You can see the spectrum is quite broad. Like it is 1420 to almost 1600. Okay, so you see that broad spectrum is there for the SOA. Okay, so by exploiting this feature, and if you just add a EDFA with this, okay, so only the thing is you have to just little bit enhance the level of this spectrum. Okay, because the bandwidth you are getting, and if you slightly enhance the label, how you enhance, like you have to combine some other amplifier, so the gain is more. So that we have achieved by we have proposed two kind of configuration. One is when the EDFA at the input stage, and when the EDFA is at the output stage. Okay, they have their own advantages, disadvantages. So then we have estimated their how they are behaving by experimentally. So then we have already carried out all these kind of experimental demonstration. So we have measured basically first we have simulated basically, so then hybrid configuration. So we are getting very good this gain around 35 dB, but the same we are getting by measurement also, by experimentally. And then this is the measure gain for the different input powers level of SOA EDFA. These are the above one is the EDFA SOA. These are the SOA EDFA when the SOA is in the first stage and EDFA is at the second stage. And then these are the measured gain and noise pair comparison for at a different pump power and at a different current, injection current of SOA, like 150 milliampere. Okay, these are the some of the results for the polarization dependent gain. So you can see here the black one is the SOA EDFA. Okay, and then this red one is the EDFA SOA, the EDFA alone. So as I have mentioned, the SOA, you can see the PDG for the SOA is the blue one. Okay, so it is very high PDG. I have already mentioned the SOA is having a very high PDG. That is why people are not using for the amplification purpose. So if we combine EDFA and SOA, so then PDG is drastically reduced around 0.6 dB. So the highlights is better gain flatness observed for the 15 dBm and minus 5 dBm input signal power. Okay, we have reported first time for comparison of these kind of PDG characteristics, and there is an improvement in PDG for if we are combining the SOA and EDFA together. Okay, these are the some of the properties one can compare for the these all three amplifiers. Okay, like EDFA, Raman, SOA. So then gain, if you can see, so in case of EDFA you will get more than 40 dB, Raman more than 25, SOA more than 30. Wavelength range is same C band in case of EDFA. Raman anywhere you can get C band, L band, S band. SOA is also like you can get only, you can choose the material accordingly for the SOA, because SOA is made of semiconductor material like 3-5 semiconductors. Okay, so if you choose accordingly you can get the gain in anywhere. Bandwidth is 30 to 60 dB. Raman I have already mentioned, it is pump dependent. Okay, wherever you use you can get the bandwidth. Then SOA is 60 dB. Then maximum saturation gain is 22 in case of EDFA, and it's 0.75 into pump power, and in SOA at 10 dB is the saturation, because SOA is saturating immediately as soon as you are increasing the injection current. Okay, so these are the like polarization sensitivity. EDFA, as you have already seen, it is 0.1, 0.2, so it's almost, if it is a single unit you can say it is a polarization insensitive. Okay, but Raman is also polarization insensitive, but SOA, yes, you have already experimentally we have already verified. Pump power in case of EDFA 25 dBm, so 25 dBm is around 100 to 150 milliwatt. In EDFA more than in Raman more than 30 dBm, and SOA is it's in form of current basically, so less than 400 milliampere. So these are the some of the comparison for the different the parameter. Okay, then I'm not going to discuss all this now, the times no more. So this airdrop multiplexing and all those things. Okay, so I'm going to directly to summary. Okay, so we have seen that measured PDG of fabricated EDFA, it was quite comparable with the PDG of commercially available EDFA. Like if you go and see commercially available EDFA, so they are also having the same PDG 0.1, 0.2 dB. Okay, the gain spectra for the multi-channel case was very different as compared to the single channel. Hybrid 2 amplifier has been demonstrated to have a low noise figure. We have also proposed a new Raman EDFA configuration, and its analysis has not only have a best noise figure but also lowest gain ripple. Gain ripple was low in case of a new configuration. Experimental simulation result were in close agreement, and we have reported first time comparison of the PDG characteristics in case of SOA. So with this, these are the some of the references. If somebody is interested, you can go through. Okay, like these are the standards books. Okay, textbook. So you can see them. So for the Raman, Islam is best. Then this Headley and GP Agrawal is also very nice book for the Raman amplification, right? Then non-linear effects, and PC Baker and Ajay Ghatak is for the EDFA. Thank you. Now the forum is open for a question, please.
Yes, from Balaji Institute.
No question, sir.
Yeah, good afternoon.
Good afternoon, sir.
Yeah.
No question,
go
sir.
Ahead. Go ahead.
No question, sir.
No
Thank
question.
you very much.
Okay. Hello.
Sir, government engineering Bharatpur, sir.
Yeah.
Sir, actually, there is an amplifier which amplify the signal.
Yeah.
Sir, what is basically, sir, mechanical system is there or optical system is there for amplification?
It's an optical system, not mechanical. Amplification is through the, similarly, if you have studied the laser, the process is same through the stimulated emission of population inverted medium.
Then electrical energy is converted into the laser system.
Actually, it is the optically pumped. It is not electrically pumped. We are using the optical pump. As you have already seen, we are using the 980 and 1480 nanometer pump laser. They are the optical pumping.
Okay, sir. Is there any method to reduce the heat generation during the laser generation?
Heat generation in case of amplifier, there is no heat generation.
So can we is there good method, any good method to minimize the heat generated during the generation of laser beam?
That actually I have not gone through, so I cannot comment on that laser system. Here there is no heat in case of amplifier.
Okay, sir. Okay, sir. Fine, sir. Thank you, sir.
Okay, thank you. Thank you.
Thanks.
Yes, from Rajkumar Goyal Institute.
Okay. आप लोगों का भाई यहीं पे हो, चलो बाहर से तो हो गया, अब इधर से समझ में आया कि नहीं आया? ये तो पूरा समझ में आ गया, कुछ नहीं समझ में आया। नहीं अभी तो इन्होंने पढ़ा नहीं पढ़ा ना, क्योंकि अभी सचान सर कह रहे थे कि आगे पढ़ेंगे, है ना। तो इट इज अ क्वाइट इंटरेस्टिंग टॉपिक, क्योंकि तुम लोग एमई में हो तो मेरे पास यहाँ से तुम्हारे जो सीनियर बैच के थे कुछ लोगों ने प्रोजेक्ट भी किया था इस पे, आई थिंक डिस्पर्शन कंपनसेशन और UWDM, PON, पैसिव ऑप्टिकल नेटवर्क्स, सो इस पे कुछ काम किया था। तो जिन लोगों को मतलब अब तो यहाँ भी कर सकते हो, आपके यहाँ भी काफी फैसिलिटी है, राइट। सो एक्सपेरिमेंट भी करके देख सकते हो। आपका जो अप्लाइड साइंसेस का जो लैब है ना, वहाँ पे काफी अच्छी फैसिलिटी है रिगार्डिंग दिस ऑप्टिकल सिस्टम्स, WDM systems. They have all the equipments, even OTDR and everything. So those who are interested can contact Dr. Chaudhary, Professor Chaudhary basically. So they have all the facility basically. Thank you.